Okay. Okay. All right. Okay. All right. So yeah. So it's first I'd like to thank the organizers. It's really a great pleasure and honor to be part of this workshop celebrating Boris' birthday and genre achievement in physics. So as you heard yesterday, right, and Boris is a master in electrostatics. So that's why I thought I would give this talk that involves some very basic properties of insulating states, the energy gap, and the dielectric constant. And also, the way we got it into this is we first were studying topological states of matter. So topology plays a role in the first part of this talk. And really, it's through this work that I've come to appreciate the richness and the subtle features of Coulomb systems, this long-range interaction. And so this work is done in collaboration with my brilliant student, Yugo Onishi, and we had a lot of fun exploring this topic. And several papers are here, and more are in the pipeline. So we know that energy gap is a basic property of the insulating states. And for example, it's very important. It determines the electrical conductivity of a semiconductor at a finite temperature. It also determines the color of absorbed and emitted light, and that's how LED works. To get light of different color, one need to choose materials with different band gaps. And in topological states of matter, having a large energy gap in the bulk is very important. Only at temperatures small compared to the gap, we get a transport from the surface states. And for example, in bismuth telluride, the bulk energy gap is 0.15 eV. This counts as one of the large gap topological insulators. And of course, the study of topology in condensed matter physics started with the discovery of the quantum Hall states in the magnetic field in the 1980s. So this is what I'm going to focus on today. This basically, the first part of this talk is about two-dimensional systems. These are quantized Hall conductivity, which I can write as C times E squared over H. And C is the ground state Chen number. And so in the case of the lambda levels in the magnetic field, when a lambda level is completely filled, we get an energy gap, which is a cyclone gap. And this energy gap sets the energy scale for observing quantized Hall effect discovered by von Cleysen in the audience. And now we also know that in recent decades, the Chern insulators were discovered in various materials in zero magnetic field. And one example, recent example, is this twisted semiconductor MOTE2. And here at the zero field, the quantum anomalous Hall states were found at filling factor 1, and even the fractional quantum anomalous Hall states were observed at fractional fillings. And for this quantum QH states at filling factor 1 at zero field, from transport measurement showed that the activation gap is around 30 Kelvin. And then there's also thermodynamic measurement by Kim Van Mack and Jie Shan's group at Cornell, and they attracted a gap of 6 millielectron volt. So this is actually the largest gap among QAH states at zero magnetic field. So so I'd like to ask this question then, how large can the topological gap possibly be? Okay, this is the interesting question. We are interested in finding large gap topological states, but is there a fundamental upper bound on the topological gap or not? So despite the study of topology for several decades, this question has not even been asked before. So I want to remind you the gap. So this is a summary of the main results. And for two-dimensional insulating states, we found that there's an upper bound to the energy gap of Chern insulators. And it takes a very simple form. It's 2 pi h bar squared n over mc, where c is just the quantized sigma xy, in units of the von Cleysen constant, h over e squared. So this is dimensionless a number. It can be an integer, or it can be take a fractional value. And n is the electron density, and m is the mass. Very simple result. And then the second part of this talk is about three-dimensional insulators. Okay, even non-topological insulators, and we found that there's also a upper bound on the energy gap, and in this case, it depends on the static dielectric constant epsilon. So this gap is basically the plasma frequency defined by the density and the mass divided by the square root of epsilon minus 1. Okay, epsilon is a static dielectric constant. And these are the main results. And I'm going to explain how these results are obtained from very general principles of physics. And therefore, these results are applicable to first case, to all two-dimensional insulators. In the second case, all three-dimensional insulator states. I will talk about non-lashes in this case. So, yeah. All right. So the way we're going to the framework we're going to use to derive these results is based on thinking about the optical response of the insulator. So let me first define what I mean by the energy gap. So the spectral gap is defined as the energy gap between the ground state and the first excited states in the energy spectrum. Now, when you shine light onto the solid, you can get optical absorption above certain frequency, and that defines the optical gap, which is the energy gap between the ground state and the first excited state that is optically accessible, meaning that this excited state must have a finite matrix element with the ground state under optical illumination. So it's easy to see by definition that the optical gap must be equal or larger than the spectral gap. And therefore, if we can find an upper bound on the optical gap, it will also be an upper bound on the spectral gap. So that's the approach we're going to take. And the basic idea is the following. If you look at the optical conductivity as a function of frequency for insulating states, this real part of sigma xx has to be non-negative. It's 0 until frequency above a gap, which is by definition the optical gap. And it can have all kinds of behavior. But one thing we know is that if you look at the whole area of this curve, the integrated area of real part of sigma divided over frequency, this is the so-called optical spectral weight. And by the F sum rule, it's equal to pi n divided by 2m, where n is electron density and m is a free electron mass. If you extend this integration all the way to infinity. So no, for all kinds of solids, this optical conductivity as a function frequency can be very complicated, but the total integrated area is very simple. Okay. Now, I want to also consider a new quantity, which is the real part of sigma xx divided by omega integrated over all frequencies. So this is really just the negative first moment of optical conductivity. Okay, so if we can say something, we can find out something about this W1 quantity, then combining W0 and W1 will give us a bound on energy gap. That's because, again, the real part of sigma has to be non-negative. So if we replace in this integral here, replace the denominator with the smallest possible value, which is the gap, then we get an upper bound to the negative first moment, which is W0 divided by EG. So combining W1 and the full spectral weight will give us an upper bound on the energy gap. So that's the idea. Okay, so how does this work? Now let's talk about two-dimensional systems, which may have a finite Hall conductivity, sigma xy. And let's consider the real part of sigma xx, imaginary part of sigma xy. These are the dissipated parts of optical response, time reversal even, time reversal odd, respectively. Now, if we consider left or right circular polarized light, and so the electric field has xy components, which are pi over 2 offset in the phase, then the absorbed power is J dot E, which is the real part of sigma xx plus minus imaginary part of sigma xy times E squared. Okay, and if you change the chirality of the light, the second term changes sign, and we know that indeed for time reversal braking systems, the absorption under left or right circular light, they are generally different, and the difference is called magnetic circular dichroism. Okay, Now, the absorbed power must be non-negative at all frequencies. So this immediately implies there has to be an inequality relation. The real part of sigma xx must be bigger than or equal to the absolute value of the imaginary part of sigma xy at all frequencies. Okay, so just using this, so so if you look at the W1, this negative first moment, I can get a lower bound by replacing the real part of sigma xx with the absolute value of imaginary part of sigma xy. I can lower bound this by bringing the absolute value outside the integral. And then this integral here is the imaginary part of sigma xy divided by omega. This by the prime chronological relation is equal to the real part of sigma xy at DC. Okay, and which is just the quantized Hall connectivity. Yes.
So that assumes that sigma xy is given by intrinsic shear number, but there are plenty of our contributions.
So I'm talking about insulating states. Insulating states with energy gap. So for metallic states, you're right.
Yes.
Sigma xy is non-quantized, but for insulating states with energy gap, sigma xy is quantized. And by definition, just for that. Yes.
Maybe this question about the next formula.
Yeah.
For the same answer. When EG goes to 0, does the result depend on how real part of sigma xx becomes as a function frequency?
Yeah, definitely. When the system becomes metallic, there's a lot of interesting.
But even before, even when
before,
EG is small.
This still holds. As this
No,
holds,
the next formula.
Yeah. No, this also holds as long as the gap is non-zero. I mean, you mean this formula? This formula always holds as long as EG is finite. When EG is 0, it's strict.
Sure.
Yeah. Let's see that. I'm going to focus on insulating states. I'm interested in upper bound. Not the lower bound. But these are all interesting questions. Okay. So this image tells me that the negative first moment of the sigma xx is actually a lower bounded part. It's a Chen number, the ground state property, and which is measurable by DC Hall connectivity. So then, combining W1 and W0, then immediately give me an upper bound on the energy gap, which is just 2 pi h1. Okay, so that's it. So so we can see that in this derivation, I've only used very general principles of physics. The fact that the absorption has to be non-negative, and the primary correlate relation, which really comes from causality of physical response. And finally, I've used the F sum rule. Okay, and F sum rule actually holds when the kinetic energy takes the form of p squared over 2n. And at a fundamental level, the Hamiltonian for electrons and solids always takes the stream. Kinetic always. So therefore, this bound actually is applicable to very general cases for systems with without interactions, for interior or fractional chain integers. It all holds.
So yeah.
Yes.
And there is all the density, right?
Right. That's
Within
exactly
bound charge.
So if we use all electron density and use the free electron mass, it is always upper bound. This upper bound is always exactly correct for solids if we use all electron density and free electron mass.
And how does it apply to Raymond?
That's what I'm talking about next. Yeah, exactly. Now, if you talk about all electron density and the free electron mass, this upper bound is very loose, so not so practically useful. But it's still good, as a matter of principle. But I think the real power of this bound becomes clear if you think about systems described by low energy beta Hamiltonians. And one example is again quantum Hall states in magnetic field, the semiconductor with parabolic bands, and we know that the beta Hamiltonian exists. Here, the M is the effective mass, and this U is electron interaction. And in this case, this Hamiltonian again satisfies the general form. Net energy is p squared over 2m, but with m being the effective mass, and then this bound still holds. But of course, here m should be regarded as a charge density, the doped charge density. Okay. Now we can see how this bound works for quantum Hall states in magnetic field. In this case, the electron density is the fitting factor times Lambda level degeneracy, and the quantized sigma xy is equal to the fitting factor, and therefore this bound just reduces to h bar omega c, which is the cyclone frequency. Okay, so but we all know that it's correct that in the quantum Hall states, we know that the optical gap is just h bar omega c, and the optical absorption occurs only at the single frequency, and it only works for circular polarized light of one-tenths by the Huang theorem. Basically,
uniform metric field only couples to the center mass motion. So regardless of electron-electron interaction, regardless of whether we are in the integer or fractional quantum Hall states, the optical gap is always h bar via c. So this then shows the general bound, right, written in terms of the density and mass and Chen number is actually tight. Okay, tight, cannot be further improved. Now let's apply this bound to twisted semiconductors, bias question. And in the case of the twisted bilayer MOT2, a zero field experiments have observed the Chen inserts on the non-Hall states. And in this case, all we need to know is that MOT2 the semiconductor with an effective mass, which is 0.62 the free electron mass. Then this immediately gives us a bound, okay, which is basically inversely proportional to the Moray unit cell area base theta. So basically, the n is the Moray filling factor divided by the Moray unit cell area, and the Chen number is equal to the filling factor. Observed, and therefore this gap bound only depends on the Moray unit cell area. So this red curve is just the plot of the Moray is bound as a function of twist angle. As we go to smaller twist angles, the base theta increases, the gap decreases, and this dot is experimental value by bias measurements. And you can see that the measured gap, which is 6 millielectron volt at a twist angle of 3.5 degree, while the bound is about 25 millielectron volt. So there's still room for possibly improvement, but at least they are on the same order of magnitude. Now, one can also apply this bound to the band structure calculations for this system, and so here I'm showing the dots are the calculated band structures for the system, and we can see that actually around 2.1 degree, the direct gap from the DFT calculations is actually 60% of the gap bound. So it's pretty good. Okay, and this also tells us that in order to design high temperature fundamental Hall states, it's crucial to go to larger angles so we can increase electron density, or we can find materials with a smaller effective mass. Okay, so the bound tells us what are possible. Okay, so in the interest of time, let me we'll talk this for 30 minutes, including questions. Is that right? 40. Okay, all right. All right. So let me briefly say this thing. Okay, to recap what I said so far, the crucial quantity is this negative first moment of optical conductivity. On the one hand, it's lower bounded by the Chen number quantized conductivity at DC. On the other hand, we connect to the energy gap. That's how we can divide the bound of energy gap based on the Chen number. Now, this quantity turns out to be very interesting. Although it's defined by the optical conductivity as a function of frequency, it seems to depend on the precise state spectrum. It actually secretly is a ground state problem. Okay, it only depends on the ground state wave function, just like the Chen number. Okay, and this is how we can see this. Basically, if we look at the continuity equation, how the charge and current are related to each other when you apply a periodic potential, and this tells us there's a relation between the sigma xx, the longitudinal conductivity, and the density response function. Okay, and in particular, then the real part of sigma divided by omega is related to basically the Q squared coefficient of the density response function. And also from fluctuating dissipation theorem, we know that the density response is related to the dynamical structure factor. So when you integrate this over all frequency, then we get basically the equal time density correlation of the static structure factor. So the punchline is that this quantity, the negative first moment, which I call a quantum weight, is actually nothing but the Q squared coefficient of the ground state structure factor. So it's a manifested ground state property. Okay. So in the same way that the Chen number can be measured by the quantized Hall conductivity, the quantum weight can be measured by the static structure factor. And physically, what it represents basically the quantum uncertainty in electrons' central mass. So if you consider a system, in simplest case, insulating states in a strongly localized regime, electrons are bound to each potential minimum. In the classical limit, right, complete classical limit, electrons are just point particles. Okay, and in this case, the structure factor would be a 0 at all wave vectors except the residual aspect. So at small q limit, S of q is actually 0. The quantum weight is 0. Okay. But because of the quantum fluctuation, electron has some certain capacitance with it, and therefore that leads to the structure factor generally being non-zero. And the q squared coefficient of the structure factor is precisely just the center of mass uncertainty. Delta P is the center of mass position of all the electrons, and delta P squared is just the uncertainty in the center of mass. So therefore, this quantum weight really represents quantum fluctuation of center of mass, and it vanishes in the limit on constant h bar W. And this was also discussed in the early days by Vanderbilt and others, mostly for non-impacting systems. But I want to emphasize that the most general way one can define this quantum weight is through the structure factor as a small wave vector. So this is generally is applicable to all kinds of systems with and without impactions. Okay. So now let me move on to the second part of this talk. So we see that so far we used the negative first moment of the conductivity. Why not extend it to the negative nth moment for Wn? Okay. And again, same trick. When we replace the denominator by the gap, we get an upper bound relating Wn and Wn minus 1. So this allows us to get a series of inequalities, and in particular non-linear equations of W2 instead of W1. So upper bound on energy gap can be provided by the square root W0 divided by W2. Okay. So the question is, what does W2 represent? Is there any physical meaning? So we see W0 is a full spectral weight related to the charge density in the system. W1 is a quantum weight because the lower bound by the term number. Now the question is, what about W2? Again, W2 is actually essentially the polarizability of the system. This is because the current J is the rate of change of the polarization, and therefore sigma is related to the polarizability pi. Again, I can use Cramer-Kronig relation, and in this case, the negative second moment of sigma is related to the negative first moment of the polarizability pi. And by Cramer-Kronig relation again, this is related to the DC thermodynamic polarizability. So this immediately gives us an upper bound on energy gap, which is basically the plasma frequency defined in terms of density and mass divided by the square root of the polarizability. Okay, so now the question is, what do we mean by a polarizability? This is where the total interaction in three-dimensional solids play an important role, which I didn't appreciate when I wrote the first version of the paper. Okay, so now let me remind you that if I have a system with a non-range interaction in 3 dimensions, there are really all kinds of 2 types of non-wavelength collective modes, right? And they couple to longitudinal and transverse electric field respectively, and they generally have different excitation energies. The simplest example is that if you have a 3D Wigner crystal, we know that the plasma frequency is still finite, it's omega p, but there are acoustic phonons which vanishes linearly at 0 and 0 wave vector limit, right? So if you have a Wigner crystal in the periodic potential, again, there's still a discrepancy between the energy of the longitudinal modes and the energy of the transverse modes. Okay, so therefore we have to be careful when we define optical response of a solid to probe the energy gap. Are we talking about longitudinal or transverse? So the answer is that we can talk about both. So far, I've expressed the conductivity that relates the current to the externally applied electric field, but this is not the experimental measured conductivity. The measured conductivity relates the current to the total electric field. Okay, and this is how the dielectric constant is defined. Now, on long wavelengths, if the wave vector Q and electric field are in the same direction, it's the longitudinal case, then the total field is the external field divided by epsilon, which is the dielectric constant. While in the transverse case, the total field and external field are equal. Therefore, there are actually 2 types of sum rules. Okay, so one is from the transverse external conductivity, the other is from the longitudinal external conductivity, and one of them involves the imagined part of epsilon, the other is related to the imagined part of 1 over epsilon. Okay, and this took me a long time to figure out. when I was teaching solid state physics for the first time at MIT, I was talking about optical response. It puzzled me why at the plasma frequency, the dielectric constant epsilon actually vanishes instead of diverges. But usually when you are hit a reflective mode, you expect the response function diverge to have a pole. But actually at plasma frequency, the epsilon actually goes to 0. That's because plasma is a longitudinal reflective modes, and it's actually related to epsilon inverse, not to epsilon, right? Okay, so anyway, so really interesting thing that in London Lipschitz,
But that Q equals to 0,
so yeah, along with that,
they should be equal.
what is equal? No, they're not equal.
Longitudinal and transverse.
Yeah, the physical conductivity is equal.
Yeah.
Physical conductivity is equal. Yeah, that's correct. Physical conductivity in the long wavelength is the same, but I'm actually what I'm using is external conductivity because I want to use external conductivity to probe the energy gap of the system. Yeah, that's key. Yeah. So okay. Anyway, so what's interesting is also that these two sum rules actually in many of the textbooks they actually talk about one of them, which is the longitudinal case, but in London Lipschitz we talk about both. Okay, in fact, the London Lipschitz is devoting most of the discussions to the transverse links, which is quite interesting. And the London Lipschitz actually obtained these results in a very different way. They were thinking about the analytic structures of epsilon, so in frequency domain, which I still haven't digested. But this is my way of finally coming to peace with this. All right, so now the same analysis will tell us that our result is that we have two kinds of energy gaps in the q equal to 0 limit. For the longitudinal gap, is plasma frequency divided by the square root of 1 minus epsilon inverse, and in the transverse case, is the plasma frequency divided by square root of epsilon minus 1. Okay, they're exactly different by epsilon, which is dielectric screening. And so if you have a highly polarized electronic material when the static dielectrons of epsilon is large, then the transverse gap must be small. And if for metal, DC dielectrons diverges, the transverse gap goes to 0. But the longitudinal gap remains finite. It actually is at the plasma frequency as expected. So now let's look at how good this bound is in practice. So we collected many different insulators, semiconductor materials, the electronic dielectric constant, the density, charge density simply just from the chemical formula and lattice constant. And we looked at the experimental measured gap, and we calculated the bound based on the density and dielectric constant. And we can look at how good the bound is. So in the case of the optical gap, which is a transverse gap, this is a table shown here. And for example, in silicon, right, very important material, the measured gap is already 44% of the bound. It's actually pretty good. But the best is a silicon nitride. In this case, the measured gap is over 70% of the bound. So this is a plot of the measured gap for various materials as a function of the density divided by epsilon minus 1. And our gap bound in this log plot is the black line, the linear line. And you can see that many of these covalent and ionic insulators with light elements that close to the bound, while topological insulators which have heavy elements with many core electrons, those are far away from the bound. Okay. And diamond is good, reasonably good. Diamond is somewhere. I don't know why it's not shown here. Diamond is reasonably good. I don't know why. Oh, we have it here. Yeah, diamond is. Diamond. And then we can also look at the longitudinal gap, which is measured by the electron loss spectroscopy. And in this case, again, first you notice the longitudinal gap is much higher, right? Much higher, on the order of a few tens of electron volts. And in this case, again, diamond and cubic-boron nitride are best, not the best. Okay, so yeah, so let me. That's all I want to talk about. I focused on the energy gap and how it relates to the logical invariant Chen number, and also how it relates to the dielectric constant. And I didn't have time, but there's also the deep connection with quantum geometry. Basically the Chen number is related to the barrier curvature, while this quantum weight is actually related to the so-called quantum metric. And this leads to many interesting open questions. And sort of take home message is that you can think of these bounds in quantum geometry as analogous to the problem of minimal surface. Like in the geometry, like we asked for a given boundary, what is the minimal possible area? And here we are asking questions for given quantized topological invariant, what are the possible minimum possible quantum weight? And that will show up in optical response. And also quantum mechanics relates length scales to energy scales. That's why a bound on the quantum weight further leads a bound on the energy gap. So and finally, separate from that is energy gap can also be related to the thermodynamic response, the dielectric constant. Thank you.
So if you have a material which is close to ferroelectric transition, the electric constant is supposedly very big. So doesn't mean that gap.
Yeah, this is a great question. So all these so you see, when I divide this bound, I used the F sum rule, right? F sum rule, which relates the full optical spectral weight to the density and the mass. So this applies to electron, Hamiltonians of electrons without coupling to the lattice liberator. So that's why this gap, this is epsilon, is really the electronic component of the dielectric constant. Now, in many materials, when they are near the ferroelectric condition, it's driven by a soft photon, right? And so in that case, the static dielectric constant can be very large, but that's not the electronic component getting large. Yeah, so it's there's a difference.
This is optical.
Yeah, that's right. Yeah, this is the optical gap probing the electronic gap. Therefore, the dielectric constant I've used the electronic dielectric constant, which in the literature people write as epsilon infinity.
Yes.
What it really means just the electronic.
Is there any use of higher moment with 1 over omega cube, 1 over omega force, etc.?
Yeah, actually, so Steve Irving told me that if you look at the negative fourth moment or something, negative fourth moment of negativity, which is negative third component of the dielectric constant, and that is related to charge distribution in the solid. There was some sort of literature about that in the old days. Yeah, just about looking at that. But I think all these moments, right, are some kind of a ground state problem or some kind of a thermodynamic response. So these are all interesting.
So in your first part, you show the calculation of the energy gap bond in MOT2 versus the true calculations.
Right.
So what does the gap difference of your upper bound and the actual calculation tell us?
Right. Yeah, that's a
Can you
great
repeat, please?
So the question is, so you see that
Enough volume.
yeah, the question is that if you look at the real materials, the gap is does not reach the bound, but there's still some finite distance between the gap and the bound. What does it tell us? It actually tells us several things. If you look at how this bound can be saturated, it's only saturated when the quantum weight is equal to the number. Also, this also requires the optical absorption occurs only at a single frequency. So both conditions must be satisfied to satisfy this bound. Now, in real systems, the quantum weight generally is bigger than exceeds this number. So this is related to what people call the discussion of ideal quantum geometry in the literature. And so that's number one. And second, even when the quantum geometry is ideal, even when the quantum weight equals a number, the optical absorption generally occurs over a finite frequency range, not just at a single frequency. So that's the second. That's the other thing. So to saturate this bound, you actually need both conditions to be satisfied: the ideal quantum geometry and single frequency absorption. First.
Derivation of the F-sum rules relies on the fact that the interaction is of the density type, so current does not couple to the density, and therefore we have a universal relation. But what if the vertex is renormalized by the Baer curvature? Can it affect the?
So that's why, this is an excellent question. So that's why we have to be careful when we talk about the F-sum rule. Just as you said, the F-sum rule holds when the you don't have additional p-squared term in the Hamiltonian, right? The p-squared term only enter the energy. So now again, this is always the case if we apply to electron in solids, the microscopic Hamiltonian, including all electrons in solids, right? It's just net energy flowing in the electron ion interaction. There's no current happening right, for the microscopic Hamiltonian. So that's why the second part of this talk, I'm really applying these bounds to all electrons. Okay, microscopic Hamiltonian of solids. And in the second part of this talk, the density is all electron density, and M is actually the free electron density. Okay, so that has no problem. Okay. Now in the first part of this talk, when I talk about the bound of topological states, there I'm using effective Hamiltonian. But in the case of effective Hamiltonians, then the M is the band mass, it's effective mass, and the density is the density of doped electrons in the low energy bands. And in that case, if you want to use this relation, one has to be careful. Applies to systems with parabolic dispersion when this Hamiltonian is a good approximation. This turned out to be the case for twisted semiconductor TMDs, because monolayer TMD is just a large gap semiconductor with parabolic bands.
Zoom. There is a question. There is a question on Zoom.
Okay,
Yeah.
Philip had a question.
So I think on the similar point that in this effective Hamiltonian case, what if the mass isn't kind of changing with the momentums, such that kind of I can
Changing
with the momentums.
with the momentum.
If effective mass can be depends on the
Okay, yeah. So this, yeah, absolutely. So there are cases where the bands are non-parabolic, right? When the bands are non-parabolic, one has to do something else. Yeah. So this is so one can still get use the F-sum rule. In most general case, the F-sum rule tells us the full spectral weight is the second derivative of the Hamiltonian with respect to E squared evaluated over the ground states.
so there's a weighted mass that you can just use
So
somehow.
for them, one can still think about this quantity. But now the thing is, this quantity depends on the ground state itself, right? So I don't have a very simple result. It's just a number. But we can actually we can further place bounds on the ground state spectral value of this inverse mass matrix. Yeah. So one can still make some progress. But it's most useful when the kinetic energy is just p squared.
I don't know how to do it.
Yeah.
It should be your computer, they say.
Michael, Misha Glazov is.
Yeah.
Question.
Yeah, hello, thank you very much for the fantastic talk. I have enjoyed it.
Oh, he can answer.
Can you hear us? Can you hear me?
Apologies.
Misha, are you?
Talk.
Question.
Okay, so my question is actually about the last part. Then you have a relation between the effective band gap, plasma frequency, and the dielectric constant.
Secondary is
Can you hear me?
One sec, Alicia.
Please repeat the question, Mika.
Okay, thank you. So my question is about the last part of your talk. There you relate the conductivity, or actually the band gap, with the dielectric constant and plasma frequency. So I wonder if you can use the same analysis for the absorption caused by the phonons, say by the optical phonons. And what would be the result in that case? Would it be just a kind of Lydon-Sachs-Teller relation between longitudinal and transverse phonon frequencies, or something beyond this?
Yeah,
Thank you.
This is a great question. So this is also related to what.
Can you repeat it?
So the question is about what the second part of this talk. What if we include the effective phonons, right? Effective phonons. So this is related to, I think, your question. Yeah, absolutely. This is something that we are looking into. And so one way to handle this is to include the lattice degree of freedom. So to write down Hamiltonian, including both electron and the nucleus. And then one can extend the F-sum rule and to include the effective lattice. And I fully expect, just as you said, I expect that in the end, this ETS relation will enter. We'll probably get something similar to the ETS. But the usual ETS relation is a equality, while here what we will get is actually inequality. It's exactly
What is ETS?
this. Yeah, this is Taylor.
Oh, yeah,
This is
Taylor
the-
Sachs, yeah.
Yeah, this is related to the
Yeah. That's in every book, in the code.
Exactly.
For
Yeah.
example.
This is related to the
Yeah.
longitudinal and the transverse phonon.
Yes, yes.
Longitudinal transverse. Now, once you have electron phonon coupling, the longitudinal and transverse phonons, they also couple to electrons. When you look at the optical absorption, there will be a finite oscillator strength at these phonon frequencies as well. So once I include the ion degree of freedom in the Hamiltonian, I expect that this can be covered. Yeah.
Expect what?
I expect this treatment can still work. This kind of a treatment can still work to give us inequalities. Yeah, inequalities.
Okay. We look forward.
Okay.
For the next one.
That was about the cells and my stuff about $1 million.
Thank you very much.
Just if somebody does unmute to ask their question, then we are listening on this app.
Thank you very much for the introduction. After the previous talk, I had a feeling I'm pulling you from the 21st century into 16th century. And they did not start with 16th century. So yesterday I was asked by students, where is Marburg? And whether we are sponsored by Philipps Enterprise. We have nothing to do with Philipps Enterprise. They have one P, we have two P's. And Marburg is here, you see it. And why we have two P's? Because this guy founded our university exactly in the 16th century. You see, in 3 years, we are going to celebrate 500 years anniversary of our university. And that's how Marburg looked like at this moment. It has never been reconstructed. The government never had money for that. So they just renovated the already existing buildings. And you see, we have 70,000 inhabitants, and every second person you meet in the street belongs to the university, and mostly it has students. And our students are really good. So there are no 10 Nobel Prize winners related to the university. Half of them are students. And this is the rating of our students. I was surprised that in physics, we share the first, our students share the first place in Germany. With T. Munich, and in chemistry, students are on the fourth place. So that's what it is about. We're a very small research group, and we're just playing toys. And we're trying to understand last year, for instance, several interesting problems. But I'm going to talk about a result which we do not understand. And this result is not ours, and the result is known since 16th century, but at least since 50 years. So let's delve into history. So it will be about this topic. And you're aware about the Spatial prize for pioneering research in physics of disordered materials and Hoping conductivity. And I'm going to talk about Hoping conductivity in its very, very classical sense. So since more than 60 years, thanks to Miller and Abrahams, we know how electrons move in top crystalline semiconductor with hydrogen-like wave functions. So for students, it's just tunneling in space. This is the extent of the wave function, and the energy is needed or released. It happens through exchange with phonons. And you can say, okay, whether anybody is still interested in this kind of research, and the answer is yes. There's huge demand in the market of organic electronics. So this is rapidly expanding market. They're already above 50 billion per year, and mostly semiconductors. And all of you have once seen such pictures. It's not only OLEDs. For instance, if you change the working unit in your laser printer, this blue stuff is organic semiconductor. Okay, and why I bring this knowledge here? Because if you open review papers about charge transport in organic semiconductors, you read there, most all of them, that transport is by copying with Milli-Abrahams transition rates, so we have something to do. This is one review, this is another review, again, Milli-Abrahams, and so on. And we can say, okay, so just open the book and go ahead. But it's not what is done. Actually, the book is not known in this community. What is known in this community? That density of states is Gaussian. So two numbers will be important for us. N is the spatial concentration of localized states, so it controls the distance of copying, and sigma is the energy spread of this distribution of these localized states. And this is a strong belief in the community that this Gaussian density of states prevents analytical solutions. And therefore, the only way to do theoretical physics is to simulate. I'm sorry, what's happening? Yes. Yes. And indeed, if you, for instance, look at this famous paper, 25th anniversary of study of OLEDs, only two theoretical results were found worth mentioning. And both were obtained by computer simulations. So, long ago, Heinz Bachelor from Marburg went from, with his group, simulated copying transport on a simple cubic lattice. Can I just? Yes. And they fitted the simulated field dependence of the mobility to this equation. And some years later, the group from Eindhoven used 1P, so from research.
Use this one if you.
Thank you, Ross. Thank you. Thank you. Thank you very much. And I can scroll it by two things. Postponing, I still have to do it. Okay, and some years later, the group from Eindhoven treated the very same problem. So simulated system was the same, the simple cubic lattice, and they also fitted field-dependent mobility with a similar equation. And it's not only a matter of academic research. There are many enterprises who develop and release device simulation packages and distribute them commercially. And all the workers dealing with organic electronics, they have these device simulation packages, just moving up there. And you see these results are pretty popular. This is not one quality, of course, not comparable, but 3,000 citations for copying transport today is something. And review articles sound sometimes as commercials. And this is from Philipps with 1P. So there is a huge demand in understanding copying transport in its classical form. And if you look at any book, yes, about organic electronics, you find this equation there, and it is really qualified as the most cited result in the context of charge transport in organic semiconductors. And this is not an old story from the 16th century. If you look at the citations of this famous paper, it's mostly in the last decade. Well, I started as a student with Boris 50 years ago. I was wrong yesterday. I counted in the evening. We met in the year 1974. It was 30, I was 20. And Boris told me already at that time, never write such equations. Because here we have electric field under the square root in the exponent. So people usually measure this dependence, float logarithm of mobility as a function of the electric field, square root of the electric field, and say we determined this constant for our material. It's not constant in some physical quantity with ridiculous dimensionality. It's square root of the meter per volt. Nobody of us are aware of such physical quantities. And what Boris told me 50 years ago, if you want to put field into exponent, make it dimensionless. And there is only one way to make field dimensionless. You just build the product, charge times field times some length, and you divide it by some characteristic energy in the system. You see there are just two candidates for this energy. Spread of the distribution of localized states and KT. The question is what to take for L. And now I address a question to the audience. What would you like to use for the characteristic length responsible for the field-dependent topic mobility in its very classical form? So hundreds of like wave functions, and here is just tunnel from one place to another place. This is just a help for you. So wide field affects charge transfer because field drops down next available localized states, and therefore it enhances topic transfer. So what is the characteristic length, students? What shall we put here? Okay. I help you. The question was answered in enormous amount of papers, and the question is answered always in the same form. Just look at characteristic length at which the drop of the energy happens. So electric field slopes your energy landscape, and you look at what length decisive drop occurs. And the answer is, of course, there is no other spatial scales but interdopant spacing. So here we put interdopant spacing, so n to the minus 1/3. Well, they did it, and this group also mentioned that the C has something to do with intersite spacing. But before we address these delicate questions, what are important length scales? Let us ask a robot question. Which of these equations would we like to use for using, for instance, for constructing device simulation packages and so on? And then the next question, of course, arises, and I think Misha asked this question already. Do they give different results? And these questions, to my knowledge, has never been compared with each other. So we did it for a couple of years, and this is the result. So this is the result of this equation, and this is the result of this equation. Okay? There is one parameter in the equations, sigma over KT. KT room temperature is 25 millieV, and the most reported number for sigma, 75 millieV. So every organic electronic will tell you it's a possibility 3. So we put 3 here, and this is the result. And they simulated the very same system, and both simulation algorithms were correct. What does it all mean? And if you go inside these studies, you learn that there was just one difference. This group simulated for localization length, the spread of the wave function, 1/5 of the lattice constant, and this group simulated for 1/10 of the lattice constant. And this parameter, localization length, is not at all in the equation.
Can you remind what is this lattice? This is lattice of localized states?
Yes, this is just hydrogen-like atom placed in the simple cubic lattice. So electron tunnels from this place to this place, and P is the spacing, the lattice constant.
But usually they think about localized states, not
exactly localized states in the very same sense as you did with Alex Epros 50 years ago, when we first met in this world. And I'm sure everybody in this audience should be surprised by this result, because we're talking about the size of the spot. So it's just this red circles are just spots, and the size of the spot, and spots are far apart from each other, so strongly affects the field-dependent connectivity. Okay, and I put here in the side spacing, and Boris claimed more than 50 years ago that the only spatial scale which is responsible for the field-dependent Hopper mobility is exactly this negligible size of the wave function. And there is no Stark effect. There is no gain of the field inside the wave function. Electron tunnels from this spot to another spot. And nevertheless, Boris claimed that this year that A is the only parameter. So he was so confident that in this paper of 73, Boris suggested to use the measurements of the field-dependent mobility in order to figure out the localization length in your material. Okay? And excuse me, I cannot skip the personal event which in fact forced me to choose this topic 2 years ago. So for a couple of years, I was a reviewer of this paper. You see the paper is published, so you can make my name open it. I was a positive reviewer. But there was another reviewer, and he was negative. Now I suggest to read carefully what this negative reviewer wrote. The authors used A with appropriate citation. They are, you get the thing. Rather than B, spacing, distance between localized layers, in the mobility expression. Appropriate citations. However, the real hopping distance is determined by the interside distance B. So the voltage drop along the hopping direction should be calculated using B, not A. Especially when A is far smaller than the minimal hopping distance, and this is the case. Okay? Well, before coming here, on the 12th of April, I got for refereeing another paper of the very same authors. And you know what they did? They adopted the opinion of the referee B, because it sounds so reasonable that the interside distance, the real distance at which energy is gained from electric field, is important, and not the toy spatial scale size of the wave function. Okay? I decided I should change my talk, therefore the title is slightly changed, and just bring the result of Boris from 50 years performance. And that's the way how Boris does physics. Yesterday, all the students already informed us about it, so let's take temperature 0. Okay, then what happens? Let's take steeply decaying density of states. So electron tunnels from here to here, but because of the slope of the length scale due to electric field, electron appears higher with respect to the reference point as in the previous starting site. How much higher? It's just charge times field times x, and x is the interside distance, so electron tunnels between the sides. The probability of tunneling is this one. And I think everybody of us would say, okay, then put here instead of x 10 to the minus 1/3, distance between sides, and this satisfied. Boris did something completely different. He said, okay, he calculates x via this expression, replaces x in the tunneling probability, and comes up with this expression, which looks as if electrons are excited, activated in energy. And that KT, the effective temperature here, is related indeed only to the localization length. For me, it sounds like head waving. I'm sorry. It's not an incident, not at all. And it's not new that people try to encode the effect of the field via some effective temperature. For instance, Kelvin many years ago did this, but then he studied free particles. They're accelerated at the length of the mean free path, then they drop phonons. So L, mean free path, is exactly the real distance at which carriers gain energy. So here it's absolutely rational. In the case here, it's absolutely irrational, because nothing happens inside the wave function affected by the field. And also long ago, 1992, already in this place, Boris with his student Mariana did the following. They took the exponential density of states from Jim Kakarios and his colleagues who know that it's varied density of states for amorphous conductors. And Boris and Mariana simulated the computer. They just solved balance equations and waited until nothing happens in the energy distribution, and traced the energy distribution of electrons, and it looked like Boltzmann-like distribution, but instead of temperature, there is something related to the electric field. And Boris was at the moment not interested what is the decisive parameter. He was absolutely confident. So the goal of this simulation was just to find out, was it correct to use this Kendravik number 0.5, or maybe this number should be different. And they found that the number should be different. It's a bit different. And then they simulated conductivity. So field-dependent conductivity at different temperatures. Everything falls on a one universal curve. if you indeed use this expression, now it was done with a final temperature. So the combined effect of temperature and electric field is described solely by this equation. And at that moment, we can still be comfortable because Boris didn't change with Mariana the ratio between intersite distance and the localization length. So being rational people who should do the following, which is okay, let us instead of A put here intersite distance divided by 3. And then everything is nice. So the length comes exactly as we expect, intersite distance, and this number, okay, it's natural. We repeated the simulations with different algorithms, with different effects. We studied non-equilibrium relaxation and so on and so forth. We just repeated their result. So it's fascinating. You simulate mobility as a function of fields at different temperatures, or mobility as a function of temperature at different fields, and then all this cloud of stars comes onto one universal curve if you use Mariana and Shklovsky expression for the effective temperature. Okay, but also, again, we were not able to answer the decisive question whether A is the only parameter. We didn't change it, we just kept it constant as Mariana and Shklovsky. Then we became interested in organic materials where density of states is doubt, and so we checked whether for the other density of states, the result is the same, it is the same, so we have fair distribution within the system. Doesn't matter what we do, this equation does work. Okay, and only 27 years after we split it with Boris, our last paper was 1990. I got enough courage to question. And what we did? The solid lines do not mean anything, just drawn through the simulated ones. And these are simulated mobility as a function of electric field, not related for a system with special randomness, and we see that result does depend on the localization length. So if you make cross-section, you fix here some intersite distance, some concentration, and you go along this data, you see the transaction length does play a role. But then we replotted this simulated data, replacing this n by the localization length. They fall on the universal curve. An experimental interesting range is from here to here. So what do we learn from this data? We fix some point here. It means we fix localization length, just the size of the spot. And we compare the results for different concentrations. So it's 2 times different distance or 8 times different concentration. Nothing happens. So A is indeed the only spatial scale responsible for the field-dependent mobility. And don't ask me why, I don't know. Okay, that's it. So Alex kind of formulated yesterday the theorem 1, Boris is always right. And I don't know why. I don't know why. That's therefore, and it is a hot topic, you know. It is used by experimentalists. It is used by device simulation. And the rest of my presentation will be about much more simple things, which we do understand. And there are students, maybe it will be helpful to learn how one can easily describe hopping transport in such a system so that it is or can be adopted by a device simulation. So from this paper, people will learn that it is not possible to make an analytical system. Therefore, all the simulations. And we have seen already this dependency. And in fact, it's possible to make an analytical theory. Just open the book of the reference, look at the chapter number 6. And you find out just 2-dimensional parameters. This is the whole formulation of the problem. You just use appropriate equations, but these equations look ugly. Electronic engineers don't like such equations. So we used another theoretical method. Was the last idea which we learned with Boris together. We didn't develop this idea, we just borrowed it from other clever people. And I would like to show to students what does it mean. So students, take strictly dependent, energy dependent density of states, put the electron somewhere and ask this electron, dear electron, where do you like to go? And the electron thinks about 2 factors, space and energy, and finds the optimal target. Why not higher? because it costs too much energy. Why not deeper? Because finally the difference is too large. So it's variable range hopping in a sense. Now you do the following. You change the energy of the initial sign, and you ask electron the same equation, and what a miracle, electron returns to the very same energy. For the deeply energy dependent density of states, this energy range is pretty narrow. And what do we get now? We have, so we did it just for Gaussian density of states. We can say it was our result, but nothing's ideologically null. And now we have the way how electrons really move in this system. This transport energy, this optimal target energy, and from any side beneath this energy, electron returns always to the same target level. And this is well known for Jupiter tunnels, definitely multiple trapping mode of transport, and it is exercise for the bachelor students to calculate the connectivity in this case. So we have just a sequence of events. The electron falls down, and then it returns, and this is the resistance in this place. And you know how to calculate resistances? Just sum up the resistances and average them. And if you have the density of states, and the time is just activation, so you have the result. And that's what we did. And of course, we came immediately to the plot form analytical formula of the dependence of the mobility on two parameters: concentration of science, translation length, and temperature. And if you do it, the result looks this way. We see dependence lie down the concentration of sites because it's variable range hopping in the range of 0.4, 0.5. And it's helpful because all experimentals measure in the diluted system, so not many electrons, this peculiar temperature dependence in the exposure. We know C, we measure T naught, we determine sigma from this comparison. So that's why we do know the energy spread of localized states in the organic materials, polymers, for instance. And just for students, how helpful is it? That's what I learned from words, to possess a clear picture of the effect under study. So many years ago, Sergei and Vladimir Arkhipov calculated analytically and correctly the temperature-dependent mobility in the multiple trapping model with the Gaussian density of states. And almost at the same time, and published it in the same journal, the group in Marburg, Schunter and Heinz-Wessler, simulated, not calculated analytically, not multiple trapping, but hopping transport in the Gaussian density of states, and they obtained this result. And then 10 years later, Vladimir Arkhipov moved to Marburg to the group of Heinz-Wessler, and they spent a couple of decades trying to rationalize this result obtained in the computer simulation. Just because they didn't have this clear picture that hopping in the Gaussian density of states is multiple trapping. Otherwise, Vladimir Arkhipov would have had immediately recognized his result and say, okay, it's multiple trapping. In fact, we didn't know about this achievement when we published, otherwise we just would have given all credit to them. And now I have a couple of minutes yet to convince you that the density of states is indeed Gaussian. This peculiar temperature dependence is observed in the empty system where you just have one electron. If you fill the system in the transistor geometry, usually a radius temperature dependence is observed. So how to bring these two results together? If people make analytical theory, they usually choose exponential density of states. This is a wonderful paper, percolation theory for the exponential density of states. Well cited, everything fine. But the authors from Philipps-Universität, they were wonderful. They do not expect anything different if the density of states is not exponential, became but steeply with some other functional form. I show you now that this is not true. So exponential tail is justified, presumably, as approximation for Gaussian distribution, generally accepted for organic semiconductor. So now, students, my message is behavior of electrons in the exponential density of states is completely different from behavior of electrons in the Gaussian density of states. Okay? So if you believe, just switch off. If you want to know why, listen. So take exponential density of states, thermal equilibrium, Fermi distribution, KT is smaller than the scale of the tail. Where are electrons? You can say, okay, I see where electrons are in the vicinity of Fermi level, which is not new for us. Why? I provoke you and say, okay, there are much more states above this level. But you answer, yes, it's fine. But the filling of the states drops according to the scale KT, so much steeper. And it means that density of states cannot compete with the Fermi distribution. Now we change the density of states. We look at the Gaussian density of states, thermal equilibrium, Fermi level, everything's fine. KT is smaller than sigma, and now electrons are not around the Fermi level. Most electrons are sitting at some so-called thermalization energy. Why? It's very clear. So we repeat this provocation. We say, okay, the number of states increases upwards, the filling decreases upwards, but the number of states increases much steeper. So Gaussian function beats the Fermi function. It's in fact the exponential shape of the Fermi function divides all possible energy distributions into classes, exponential and Witten. Then we have normal distribution of electrons close to Fermi level, or steeper than exponential. And then the third energy appears in addition to Fermi level and to the transport energy, and this is this thermalization energy. So in the exponential density of states, so beloved by analytical theories, you bring electron and it goes in time deeper and deeper and deeper and deeper and deeper and deeper and deeper. And this means mobility depends on time. Well-known dispersive transport mode. So no stable one particle picture. So in course of time, the distribution of electrons in energy dives, and you can stop this diving only one way. You fill the system, and it means that mobility will be always dependent on the concentration of electrons in the system. The Gaussian density of states will have this thermalization energy, and as long as Fermi level is far below this energy, electron mobility doesn't know anything about the concentration, because the important sites, remember, multiple track encryption, and the average of times is governed by this energy, and these sites are very poorly populated. Electrons don't see each other. And this is not new, because it's also produced by computer simulations. So you distribute electrons randomly along the energies, and you trace the evolution of the distribution in time. And when electrons, the distribution arrives at this thermalization energy, distribution doesn't change. And it means exponential density of states is in fact bad density of states to treat, because mobility is time dependent and concentration dependent. In the Gaussian density of states, we can make zero for a single electron in your system. It's very comfortable. And if you do it, the following explanation comes. So this is experimentally measured dependence of the mobility on the concentration of electrons. You remember in the exponential tail, mobility always depends on the concentration of electrons. It's always between Fermi level and the mobility edge. And in the experiment, mobility doesn't depend on the concentration at low concentrations and does depend at high concentration. And it's easy to explain. So at low concentrations, Fermi level is far below this thermalization energy, and all everything happens here. But you fill the system, you increase the concentration of electrons, and at some particular concentration of electrons, this Fermi level they can process the thermal equilibrium function, and from this point, mobility starts to depend on the concentration of electrons. And this is not a unique feature for the Gaussian density. I've already mentioned this is a feature for any density of states with this number p larger than 1. P1 means exponential density of states, P2 means Gaussian density of states, but P 1.5 also would show concentration independent mobility at low concentrations and dependence at high concentrations. So how to determine P? Very easily, you see this equilibration energy depends solely on this P, on the density of states. And Fermi level is determined by this number P, by density of states, and concentration of electrons. So I just look at the experiment at which experimentally observed concentration N for which P, these two energies come together, and the result is P is approximately 2. And from this point, you can do everything what you like. So you can calculate temperature dependence. These are now solid lines produced by analytical theory. And points are computer simulations for special random systems and so on, and it works perfectly. And if you want to study the dependence of the mobility on that concentration, you just insert Fermi distribution in your very simple equations, and you get the experimentally observed data. Solid lines now are not just for our eyes. These are results of the analytical theory, and points are computer simulations. And now the key question comes: how to describe field dependence? And it's not possible in these simple and waving pictures. So the only way to do is to take the effective temperature from Baronovskii to insert this effective temperature, field dependent and temperature dependent, instead of temperature in your simple theory, and the result is this one. Now, solid lines are the results of this action. So it's analytical theory using Shklovsky's effective temperature. And points are simulated results. And the conclusions are very simple. Analytical theory easy. And why A and not N to the power minus 1/3, I do not know. But I know the theorem. Shklovsky is always right. I'm sorry. Thank you very much.
You reminded me, actually, in one dimension, you can journalists here. I have a paper, around 2005.
Speak up.
And the coefficient, by the way, is not 1/2, it's 1/8 in 1D.
Well, now let's explain what we're discussing. So I told you, in order to calculate 2 dimensions, 3 dimensions, you just sum up resistances and average. Like if you go to the electrotechnical laboratory and measure. And one-dimensional case is exactly this situation. It doesn't matter multiple trapping or whatever. You have just one direction. So you have to go through all steps. And now, excuse me, my last discussion with Alex Efros, who was in fact my formal advisor. Boris was just person from formal. And Efros told me at previous conference, it's not possible because in one dimension, resistivity is infinite. Because Gaussian function or exponential function never stops. So you always come into barrier with infinite path. The probability. Yes. Well, yes, but now the probability to have this mountain is Gaussian. And the difficulty with this mountain brings into your transform is exponential, it's just activation. And therefore, mathematics is exactly the same.
Well, we can discuss it.
Okay.
I understand. Can you explain what M is?
N is the concentration of randomly in space distributed.
No, and small.
It's concentration of layers.
And they're created by light, right? Electron.
No. It's transistor geometry. So they fill the system by get voltage.
They inject.
Yes, they inject.
Electrons are injected. Okay.
Yeah, I guess people want to get the proper break.
Thank you.
We discussed with you, and you were, I guess you.
Oh, good.
Morning.
Yeah, please.
Spatial. It's 30.
8:30.
I'll try to make it. It's hard work. But you live very close.
Yeah.
I need to drive 10 minutes. I need to get up even earlier.
Sundays,
It's probably
Yeah.
simply that. Simplest one.
usually the same person. Yeah.
I see.
Yeah.
Because don't wake up that early.
I wake up very late actually. I'm running late.
Yeah.
That's good. That's actually. People say, you know, in the evening when you study or when you do work, that's actually when the mind is
Depends. Some people. I think some people, but I think there are two ways. One, some choose to do it in the very early morning. It's very quiet, right? You get to the office at 6 a.m. or something. Some stay very late and also really quiet. Just like whether you want to that quiet period at the beginning of the day or
that's right. And there is, I think, second order advantage of evening. They say because that's when your brain is trying to consolidate the memory to accumulate it. So it's best for learning. That's what I heard.
I see. Okay.
Yeah, I do some writing in the evening.
But the problem sometimes is, evening is actually immediately after dinner, you're not very good.
Immediately after
But then you know, after a while you become awake again.
I don't know if you know Adam Ray. So,
Yeah. Good friend of mine.
Yeah, good friend of mine as well. Yeah, he's like a 11, but then he told me one of
So
the.
you guys overlap during the postdoc period, right?
I overlap with him for the postdoc. He didn't. I started at
But then you guys never really overlap.
Good friend with when you know we talked a little bit. I invited him for talk. Waterloo, yeah. I saw him last time at.
But it's singular, so.
About the fancy footage from his house.
Yeah, he's very fancy. I shared the room when I was in the conference. One impressive me, like he brought his he drove like for many hours and he brought his Nintendo Switch and asked me to come with his. He knows. He knows the meaning of
He bought like a $12,000.
Hardcore one.
Yeah.
I guess
It's a professional grade. Yeah, it's like a, it's really like people using computer. And he bought maybe even the more expensive plan. Yeah, he bought it's from piano and also pool. Now he joined a local pool league. So it's like
he's doing
it's very much
seriously okay. That's very impressive. Adam used to tell me that he because he wake up late he automatically get into this healthy cycle of intermittent because he skipped so much
Yeah. So I think that's
but people are studying really when we naturally without even trying your feed 2 meal and that was supposed to be very healthy. I heard.
right?
Like meaning very nutritious. I try to see
well, still, I see that the lines are kind of
breakfast. Lunch and no dinner. So I
So size,
but I can mix correlation.
Nothing.
So I wake up at 6 a.m. and I wake up. I'll wake up early for your podcast. But I know because I did the control stuff.
Calculation actually happens basically.
Mine is a little bit clearer. I think maybe play safe.
I think that
as long as it works. Yeah, I think that's a good thing. So I forgot like you get 1 hour.
Chart speaker as well.
Yeah.
That's it's earlier or
Special angle, there is this kind
It's
of.
Like
that's-
9:30.
Yeah, yeah, it's 9:30, so it's
Yes.
not that- but still, it's earlier than 11.
It's okay.
80 degrees
That's
also,
fine.
there is a bit of the behavior.
But that hotel
try
is
to
nice.
lock
When I interviewed
Right.
here, I was in that place, the hotel.
Actually,
Back
I
then it
expected
was
some
called,
of the performance spectrum things, maybe do
university
something
hotel. Now it's
interesting
for
around that
because
angle.
you may notice that.
That's basically-
Yeah, lots of
reception-
students.
yeah, and even the
Yeah, lots of-
receptionist,
This is.
they do it for,
Are they doing like a school or?
Basically,
it's not good. I remember I gave a talk at
Yeah.
Purdue.
it's a business which is.
Specialty
They did,
Yeah.
okay.
So the students actually work in the
It
hotel.
never.
I see, I see.
They actually
Is this,
Yeah.
get-
There is a special.
I see, I see.
yeah, there is a-
they pay to serve actually. We are sort of joking that they pay the tuition to serve other
And
people.
those are typically the best, best.
well, this we
like
can
a
do
guest
some,
can- Because
I can zoom out.
the GPA is high,
Yeah, yeah,
you know,
yeah,
the
yeah.
surveys I should, you know, the
Also
similar
that-
thing I was
that-
gonna say, like, was
Purdue.
Purdue also they have. You know,
Yes.
management department and all the students are doing it for the courses.
Right,
They
they
are
actually
paid
go
to
back
serve.
into-
Yeah, yeah.
But the service is one of the best that
Yes,
I
it is.
ever received. Yeah. Pretty impressive.
Yeah.
Did you also get some?
Yeah.
Yeah, several common nodes.
Yes.
Yeah.
And topology, electron in the nanotube.
Yes,
I
yes.
believe that node, that just the gauge node plays an important role to determine the electron donor couplings in the nanotube case.
I think actually, it first appeared in theory in Ando's paper
Yeah.
on actual nanotubes. So as far as I know, this idea about.
Maybe that I get confused about that, yeah.
Yeah,
One
so-
is relevant, the other one is less relevant. Yeah,
I think it goes back to Anto.
yeah.
Actually, that it was the.
Yeah.
Try to use one.
Yeah. I guess that if you're interested that the guy that who actually carry over these things into forms and on this Ando's calculation is a Mr. Kushin. Yeah, he's I believe he's in those training.
I see.
I think he's the guy that does a lot of this thing, and yeah, including the basically he's the work that Anto did of
Yeah,
is basically with so he's a guy that he had some of this paper about performing things and things. So if you're interested in that,
Okay.
he's the right time.
Question.
Yeah.
Thank you.
Yes, that's very good.
Question, yes, yeah, he's in course of the papers.
Yeah.
Well, you have lead. That's something somewhat similar has happened with Caltech. Caltech, believe it or not, last 7 or 8 years, has started to admit students in the Park Place. Caltech? It's laughable. It's laughable. But somehow I've been retired for almost all that period, so I'm really tuned in. So you go to the gym a lot, it's like some year of it, and they hired some director of athletics years ago. Whose mission was, Caltech needs to win more tournaments, games. What the hell are you talking about? And it's had a direct impact, according to the people that I talked to that teach, in terms of quality of students. This last winter, occasionally act as a TA in physics, because I find it entertaining with the little kids. It's nice. It's like fun to do. The level of the course has declined from that. It's like it's not part of the public high school. No, it isn't. And I wasn't taking a AP course. It didn't exist back then. So it's
really nuts. It needs total reformation.
Yeah.
So Ray was telling me about the decline. You seen it at Caltech too?
Well, I'm not very well tuned into it anymore because I've retired.
I said, not in the front lines.
Certainly. I haven't been on the admissions.
ages and ages. But general thing seems to be, like Ray was saying, that there's a spike of students at the top end, which are astronomical.
Always been, always will.
Always been, hopefully.
That's
But
the
now
area
there's
under that curve is.
But now there's a
That is
blob,
right.
there's a blob down lower instead of an exponential tail.
We have a new dean that has been pushing, increasing enrollment in the College of Science and Engineering. That is up by 10%, also do another 10%. And insisting that it's not going to degrade quality. I mean, we're pushing back a little. I mean, so what has happened is there's like 1,600 students that come into the College of Science and Engineering this past year. They don't all take Calc 1, so I don't repeat classes. They don't all take general chemistry. They all take intro physics, the physics for scientists and engineering. And we don't have the lab space, the teaching labs for 1,600 students. You know, we all really get more students in there. I say, for example, the profile is driving the fire engine. You know, it's ridiculous. And so what we're actually doing.
That's a very different problem.
No, I know, but we'll see whether, well, there's also the separate issue about. I mean, to some extent, we were kind of like making an allowance for COVID because, you know, you're getting high school people who did their high school online and stuff. So that's gonna start working its way out and we'll be able to get a better read, I think, you know, this coming year and going forward. Because those students are now taking computer classes, so they know this.
So probably good down.
Yeah, right. Yeah, I gotta get ready and have them.
I was telling you that music trend. Very new. I've worked 5 and 7 years. Starting to care about students' athletic.
Really?
That's pretty hilarious.
Yeah. So.
That is pretty.
I had a friend who worked at the comic book shop and he had gone to Carnegie Mellon and he knew that I was from Chicago, University of Chicago. And so we used to have a joke about which school was better, depending on like which football team lost more.
Caltech can find you guys out. Let me tell you, a few years ago, it made national news actually. No, this is several years ago. Caltech basketball team managed to win a game.
Really?
After having lost 300 in a row.
No.
300 and something. Yeah.
Really?
What a tragedy this was. They had this.
I know they have this spectacular, right? I know.
National significance.
Could never be matched. Really?
I need to think about it, but let's stop. Yeah.
Okay, thank you very much for having me. I was gonna tell my board story, Steve boards.
He'll be in a second.
Well, maybe I'll tell it at the end. Yeah. So what I'm gonna tell you about is time, momentum, and energy result both tunneling spectroscopy. We have a kind of spectroscopy that in a way can do a lot of what optical pump code can do, and I'll show you how that works. To get there, I'll tell you the basics of our tunneling technique, which involves applying sudden electrical pulses and looking at displacement current flows. This stuff. Okay. So. Yeah. So okay. Here's an outline. Now, first, I'll tell you about just energy result tunneling on a hall. Then momentum and energy result tunneling, and then spin result tunneling, and then time energy and momentum result tunneling. But then finally, if I have time, I'd like to connect a little bit with what
talked about yesterday and tell you about some crazy things on edges. So the simple approach to tunneling might be to make a contact and sort of a 3D metallic system and a 2D system, and then just apply a voltage and look at currents. In gallium arsenide, this actually isn't possible because you end up shorting out that tunnel barrier. And the other thing is when you apply currents, of course, you get heating. Apply voltages, you get heating.
We prefer to select.
Oh, sure. When you apply voltages, you get heating, and you also get you also get gating. You also get gating in this system. So this creates issues. The best thing to do is actually not to make a contact and to make sure that your tunneling is purely vertical. The transport is purely vertical and there's no horizontal component. This actually lets you look at tunneling into insulators, which is pretty interesting. So what we do is we apply a voltage pulse across this capacitor structure. There's a thin tunnel barrier here and a thick barrier here that doesn't allow tunneling. And when you apply the voltage pulse, you drive charge into this 2D system, and then you can detect image charge appearing on the opposite plate. So in gallium arsenide, this is just done by having a quantum well here and a tunnel barrier and so on. So now if you try to do this and try to measure that image charge, you see a lot of noise, but if you average about 250,000 times, there's a signal there. You fit the initial slope of that curve. That gives you 1 point on an IV characteristic. And then you can trace out the full IV by just varying the pulse height, positive or negative. This is where we were in the 1990s when my student Huang developed this. He's now a professor at Hong Kong University of Science and Technology. Then Oliver Dial, who's now the technical lead for quantum computing at IBM, which is pretty good, so he's a good guy. He made it so that we could actually take a derivative of this. What's really hard to do is to get sufficient precision in the voltage that you apply when you apply a pulse to have it be really flat and not ring. So he enabled this step. So if you take that DIDV, that's a tunneling density of states, and you apply the peaks of it as bright and the dips as dark, you can make this column here. If you step the gate voltage, you can change the electron density, and you can just keep doing this and build a spectrum. This axis here is pulse height, and this is again density or gate voltage. Here is the Fermi level in gallium arsenide. This is at 4 Tesla. And this up here is what you see from injecting charges. So these are empty states above the Fermi level, and these are filled states below the Fermi level. This is filling factor 0, empty system, filling factor 2, filling factor 1 with a big exchange gap. I don't have a lot of time to talk about this older work, but I'll just point out one thing is that if this is at 1 Tesla, and if you look down at very low densities, you see very many Landau levels. As you turn up the electron density, these things sort of disappear, they broaden. And the reason they broaden is because as you turn up the density, you have a Fermi C, and electrons can lose their energy to the Fermi C by creating particle hole excitations out of it. So the lifetime drops. So a couple of features of this tunneling that I really like is that there's no heating because we apply very short pulses, about 100 nanoseconds, and we can wait microseconds for the system to cool down. So what you're seeing is really the ground state spectrum of the yep.
So this noise that you see, is it electrons going back and forth between your
which noise?
In the initial
that's just experimental noise, just amplifier noise.
Amplifier. Okay, so it's not just the actual electrons going in and out of the system.
We have. I'll show you things hopefully at the end where we actually can look at single electrons. But implementing this at the single electron level is tough because there's just not a lot of signal. But let me go on, and I'll show you that coming up. Okay. The other thing that really gets me about this method is that there's no gating effect of applying a voltage pulse. So typically in tunneling, and you have to really watch out for this in things like SDM, is that you are gating with the tip as you apply a voltage. In this, the axes remain precise because you were only looking at the initial surge of current before, so there's really no density change in the system. The energy resolution is only limited by the sample temperature, and the observed spectrum is a ground state property. So we went up to higher fields. This is 13 Tesla, and you see chemical potential jumps from fractions. You see these other features that arise from tunneling into Haldane pseudopotentials. Alan McDonald calls those these Haldane sashes. But the sad part about all this was that the energy resolution, it's supposed to be 10 microvolts or something. We're not seeing, because it's only limited by temperature, but everything here is kind of blurry on sort of the half millivolt scale. The reason it's blurry is that the electron lifetimes are short. So you put an electron here and you get a big broadening because it decays very fast. So at some point I started thinking, well, this is really sad. We're never going to see anything sharp. But we got lucky. We went and studied the 2D hole system where electrons are heavier and more likely to form Wigner crystals. And so what happened was at happy face, because we saw something, there's this blurry stuff, which is again just due to short electron lifetimes. But around filling factor 1, there's this very sharp feature that appears, and it has this funny asymmetry. It's a dip here and a peak here. This is actually a signature when you have that of some kind of phonon dressed tunneling. And indeed, we think it is a phonon. We think this arises from the phonon spectrum of a Wigner crystal that forms at filling factor 1. It actually is extremely temperature dependent. So if you go down to 20 millikelvin, you see this thing very clearly. And just taking this line cut, as you go to 200 millikelvin, it's completely gone. And that shows you the evolution. Now, the semi-classical prediction says that as I move away from filling factor 1, if I have vacancies that are forming a crystal, the energy of the phonon should go like density to the 3/2 power. But we have this sort of strange stiffening in this thing. As you approach the 4/5 fractional quantum Hall state, the thing stiffens. I don't really understand why, but a referee actually keyed us into a paper by Janendra Jain, and this is a fit with only one adjustable parameter, which is a vertical scale factor to Janendra's paper. If someone can explain to me why the Wigner crystal stiffens as you approach 4/5 instead of just melting and going away, I'd like to know the answer. I never really figured that out. Okay, so then the next thing we did was to do double well tunneling. So we're going to have an isolated system of 2 wells separate, so there'll be tunneling between them, but then we'll have thick barriers on both sides. And so we can tunnel from a small Fermi surface in what we'll call the probe layer and into the target. So this size of that Fermi surface sort of determines our momentum resolution on the other side, and we'll apply a parallel field that we can use to steer around this little Fermi surface spot. And if you do this just on an empty quantum well, when the target is empty, you end up seeing the 3 lowest subbands, and of course they're parabolic. It's not too exciting. It's more interesting to turn on magnetic field and to see the development of Landau levels. What you're seeing here really is the overlap of electrons in the n=0 Landau level in the source well tunneling into the target, and you need a momentum shift to tunnel from n=0 to n=1, and that's what you're seeing over here. All right, so then the next step we did was spin resolved tunneling. So if you think about filling factor nu=2,
You control momentum?
it's simply with a parallel magnetic field applied this way. So we can steer that around and map out momentum. Then we had spin resolved tunneling. And the spin resolved tunneling, you can consider the filling factor 2, where we have equal numbers of spin up and spin down. If you're filling factor 1, there's this big exchange splitting, and we can use that as a spin filter. So the idea is that we're going to tunnel into this filling factor 1 state. So we're going to set one of the wells to be a quantum Hall ferromagnet at filling factor 1, and the other one we're going to vary the electron density in it. That's this axis here. So I'm going to vary the electron density in one of the wells between filling factor 0 and filling factor 2. And what you see happens is when you get to filling factor 1 in this well, you see a dark line in the spectrum, and you also see that at 2/3 and at 1/3. So what's happening is that when you're at filling factor 1 in this system, there's no room for spin up electrons in the system that you're tunneling to, and therefore there's just no current. There's no tunneling current at all. So this is a measure of the spin polarization in this. It's actually a really good measure of the spin polarization in this system that we're interested in, because it turns out there's a sum rule where if you integrate the tunneling current over a Landau level, you actually get a number which is proportional to the number of spin down electrons, since only the spin down electrons can tunnel. And from this, you can then extract the spin polarization. So this is the integrated tunneling current, just integrating vertically on this axis, on this energy axis. And then you can convert that directly into spin polarization. You can see things right away, like the skyrmion peak at filling factor 1. And then you can see that in this case, filling factor 2/3 is spin polarized, filling factor 1/3 and below is spin polarized. So this sort of very pretty picture emerges. Now you can do this also as a function of magnetic field strength. So here I was varying staying at fixed field and varying the filling factor. What we can do here is also step the perpendicular magnetic field. We have things happen like filling factor 2/3 goes from being unpolarized to polarized. The thing about this is it fits theory so well, composite fermion theory so well, that it's actually kind of boring. Everywhere you see here that the predicted spin polarization is sort of what you expect, and the skyrmion is there and what you expect. Now, the thing that's different is if you go up to the next Landau level and try to apply the same composite fermion theory, free composite fermion theory, it absolutely doesn't work. Filling factor 5/2 is basically everything is spin polarized except where it's supposed to be spin polarized at 7/3. And what we find here is a 5/2 is polarized down to as low as we can measure. And so this is just a comparison between free composite fermion model and what we see, and they're just radically different in the second Landau level. Okay, now the next piece of this is to add time to do sort of a pump probe spectroscopy. So what we're going to do is apply a pulse sequence, and again use this sort of 2-well system. This is really kind of like a lot of optical spectroscopy that has been done in the past, except that it's all electronic, which is a new thing. And the other thing that's different is we can really precisely inject electrons into a particular electronic state, whereas optics will, excite anything with energy difference that's the incoming photon energy. So again, we're going to use this sort of same picture of two wells and a point-like source. But I'm going to do this in magnetic field, and what we're going to do is have the source well be in the lowest Landau level and at low filling. So filling of Landau level filling of about 0.3. So this is spin polarized, and we're going to tunnel into the target on the other side. And what I'm really going to focus on is tunneling into from the n=0 Landau level into n=1, and to watch what happens. So we'll say much of the time it's some fixed momentum kick that allows tunneling from n=0 to n=1, which is what's happening around here. And the setup again is we'll apply a pump, some delay, and then we'll probe to see what goes on. And we can watch this in time as we set the delay. And what you'll notice is that this is the sort of spectrum that I showed you before. but it's at small time delays, there's this yellow feature. That yellow feature has to do with charge tunneling back from the target back to the source. I'll show you how that works. So now what we did in the pump is we're pumping from n equals 0 to n equals 1. And then we're going to, but these are excited states, and the target we'll see will vary its DC electron density, and you'll see that the decay, the energy decay from n equals 1 down to n equals 0 depends on the density in the target. Now, what happens is with that yellow feature that you saw in the spectra, this yellow feature right here, what happens is that this is actually from electrons tunneling back during the probe pulse from n equals 1 in the target to n equals 0, to n equals 0 in the source. There's a difference between the energy to tunnel in from the source to the target at n equals 1 and tunneling back, just because of charging effects from pulsing one way or pulsing the other way. So this yellow feature actually tells you how many electrons exist in the remain in the n equals 1 Landau level that we put there. So again, as I mentioned, this is this charging shift. It's a trivial effect. Why there's a spacing between the red and the yellow that you see. Okay. All right. So now what we can do is look at this this is at a particular momentum cut. So we can vary lots of things. We can vary the momentum kick in tunneling. We can vary the filling factor. We can vary the probe energy. So this is the n equals 1 Landau level here. And as you see, the only place where you see yellow between 0 and 1 is right near 1, filling factor 1. And that's because electrons, when they're pulsed into n equals 1, rapidly decay into n equals 0. However, if you go beyond nu equals 1 in the target, then the decay is also rapid again. It's only slow around here, but it's also slow as you approach nu equals 2. So you start to see some yellow stuff as well.
Hey,
and yeah.
How do you provide a terahertz probe energy?
It's not so the energy level, the energy here is set by the pulse. It's not set by
just the height.
Just the height of the pulse. So that's the sort of the beauty of it, is you can sort of pick and inject. You know, that's, of course, it's a hard sample to set up. It's not trivial. So it's not as flexible as optics, but when it works, it's got some real precision to it. So what we have here is, if you look as a function of time, the yellow stuff goes away, and this is happening because we're seeing a decay from n equals 1 to n equals 0. Also, if you go to a higher filling factor, closer to filling factor 2, where we also believe the system to be as spin polarized as it can be, then the decays become very long, sort of 10 microseconds or so. And you can fit to these, and they are, in fact, decaying exponentials. So what we can do is plot the time constant for the decay, and what you can see is that around filling factor 1, the decay is slow, but then when you get past about 6/5, well, it becomes very fast, too fast for us to measure, and then as you approach filling factor 2, it the time constants become long again. What's interesting is that in terms of the spin polarization curves that I showed you, this is looking between 1 and 2 in this white region here, just like this is here. And you see that here where the system is spin polarized, the times are long, and then the times are fast where this system is spin unpolarized, but then as you go up this curve. So clearly this has to do with spin, the decay rate has to do, and it makes sense that it should have something to do with spin, because we're injecting spin up electrons into the n equals 1 Landau level. They have to flip their spin. If we're at nu equals 1 in the target, then what happens is that this guy has to flip its spin in order to lose its energy. There's just no room for it otherwise. So what you're really seeing is some kind of spin flip relaxation time. So that's what's happening there, and that turns out to be on the order of microseconds. Okay, but then there's and then here it turns out, basically as you approach nu equals 2, you're diminishing the number of available. It's both spin polarized, and there are not very many available states since the Landau level is almost full. And then the relaxation times become very long, and this is how we get the sort of 10 microsecond time. Now, if you pump hard on this thing, so this is a small, or without any pump, you just see the Landau levels as before. If you, as you pump hard on this thing, you see that this Landau level, this n equals 1 Landau level actually broadens, and it turns into something slightly different. What's interesting is to stay at fixed momentum, so we'll stay at this red line cut, and then look as a function of pumping strength, what happens to the energy of that state. And there's an interesting and sort of perplexing transition. When we saw it, we didn't really understand it, that you see that as you pump harder and harder, and this is pumping up to about 10 to the 10 electrons being injected into the n equals 1 Landau level, that there's a crossover, and there's this funny splitting that you see, and we sort of puzzled for actually many months about what is that splitting. I think we understand it with the help of Pavel Havelak and his group at University of Ottawa. I think we know what it is, and let me explain what we think it is. First of all, what it is not is a change in the static density. As you pumping 10 to the 10 electrons in a system with about 10 to the 11 electrons, that you might think might have some effect where things shift. But if you just look at what happens if I change the DC static density in the target well, there is no such shift as I move away from nu equals 1. So this is nu equals 1, and I move the density up just by changing the DC voltage across the structure. I don't get this splitting. So this splitting is some kind of interesting non-equilibrium effect. So you can watch that splitting, and it goes away with time, and it goes away with time at about sort of microsecond time scale, a few hundred nanosecond time scale. So what is this thing? What we think it is fairly straightforward. So again, we're injecting spin up electrons into the n equals 1 Landau level, but to go into to decay, they have to flip their spins, and what we have is a flip spin trying to get into the nu equals 1 state that's below. Let's call this state nu equals 1 plus, where we have a flip spin that hasn't really been incorporated into. I mean, we're in some kind of non-equilibrium state. We haven't yet relaxed fully down to the ground state. The ground state should be, in this case, a skyrmion. And Pavel's group, what they did was exact diagonalization calculations. This just shows up here that if I have just one spin flipped and I have 8 others that are spin up, then it doesn't really matter where I put this spin in terms of its angular momentum. And the energy doesn't change because the whole thing is just spatially invariant. But ultimately, if I wait over time, I'll start to form a skyrmion, and I'll come down to this spin 1/2, total spin 1/2 state for the whole thing. So what happens is this non-equilibrium state has an effect on the spectral function for tunneling into the n equals 1 Landau level, and it shifts it up. And so before you did the pumping, you had this spectral peak for the ground state of the target well. But once you've done the pumping, you have this nu equals 1 plus state. And what's happening is locally you get little patches of nu equals 1 plus because we're pumping at sort of this level of up to close to 10 to the 10 per close to 10 to the 10 per square centimeter. And what's happening, the reason for this crossover is when you have small pumping, you have only a few spots that are in this nu equals 1 plus state, but over as you increase the pumping strength, when you're at 110 to the 10, you have sort of nu equals 1 plus on average states that are about 100 nanometers apart, and they sort of fill the space. And so you undergo this transition from tunneling into sort of ground state of the spectrum of the 2D system to tunneling into this funny non-equilibrium state, which over time relaxes into skyrmions. So these are the people involved in this work. I was going to go ahead and talk about quantum dots if I have a few minutes. Are there any questions on this section? Yeah, Philip.
So in the beginning, you mentioned that usually this tunneling bias induced the gating effect is not there because we extract the charges rather fast. Now this pump probe, now I start to see that is there any effect coming from this biasing effect?
Well, so we're pumping hard, and we are getting a sort of a gating effect because we are actually changing the amount of charge in the system. So yeah, the early stuff I showed is really pure because if you think about the time to equilibrium would be like milliseconds in this sample, but we're only measuring over 100 nanoseconds, so it's just fast. So yeah, but here there is this is kind of there's a bit of the gating effect, which is why I showed this thing down here to see what would be the effect of gating. And the effect of gating is nothing in terms of doing funny things to the spectrum. But the effect of putting in non-equilibrium electrons into n equals 1 is something else. It is creating some kind of new state. Right? What's really fun, it was really fun to work with Pavel, because, and he's sort of the obvious person to look at because he's done so much optics work on 2D electron systems. And so this was kind of a novel thing for him. Hey, no, we can really inject into a particular state. You don't have to worry about all the other things that could be going on. All right. So any other questions on this? Yes.
Sorry, very, very dumb question. So how do you convert, like how do you like assign those momenta there? Like in your measurement setup, could you please go over your measurement setup? How are the measurements performed?
Okay, so what happens is, how do I have to go way back? So what happens is that let's see this picture, right? So we're tunneling from one well to another, and if you have a magnetic field applied parallel to the 2D systems, there'll be a Lorentz. It's just it really, the amount of momentum kick is just the electron charge times the magnetic field times the distance between the two. So it's just integrating the Lorentz force. That's all it is. And this allows us the ability to do shift. The first person who worked on this was Jim Eisenstein, actually in parallel wells, and showed this. Liang?
One question. You're applying a voltage pulse, so everything can be measured in time domain. So I wonder if this related to some kind of a sum. Can one think about some kind of sum rule? It's usually people measure like tunneling in frequency domain and
right. So the picture that I have, my sort of very brain dead sum rule is that what we're doing is filling space with this nu equals 1 plus state. I don't know. This is sort of this magic density about 1/10 to the 10 per square centimeter, where on average the electrons that have dropped into the n equals 1 lambda level with the wrong spin, they're on average about 100 nanometers apart. And somehow this is where the crossover happens. If we couldn't go to higher density for experimental reasons, but if we could, presumably, if you keep going, you just get all this upper state and none of the lower states. So this I'm sure there is a sum rule associated with this tunneling because it really is looking at spectral overlap. So I would be very interested in your thoughts about that. Okay, so let me continue and tell you about an old story with quantum dots and then related to new stuff. So long ago, we learned how to sort of do this kind of tunneling, but at the single electron level. And this is actually what got me my job. So we were able to look at capacitance peaks from electrons entering this thing one by one. And it's sort of down here, it's sort of, we called it artificial atom physics, and then it turns into Coulomb blockade. And this is very interesting for a small dot. Now, if you made a larger dot, things were really dominated by disorder. There's sort of a capacitance step from adding electrons into this thing and filling it up. But if you look at the base of that step, you see these sort of random electron additions into localized states. And the really weird thing that happened that we noticed right away was that you had crazy pairs for tunneling where two peaks were right on top of each other, and we couldn't understand how this could happen with localized states, and I think we still don't really understand this at all. Although Leonid Glasman, who's also in this room, heroically came up with a model that I think was really beautiful and may still be the result, may still be telling us basically what's going on, but there's a hiccup, and I'll tell you about that. So the idea was, imagine you have 4 localized states, increasing energy from 1, 2, 3, and 4. So you first occupy this guy, but then if you put an electron here, the next one should go there. But if you try to add one here, now you have Coulomb repulsion between these two, and the one that was at 1 moves to 3, which lowers the energy at 4, and then an electron gets drawn in. This is called a negative U model. The problem with this thing is it kind of latches, and so once you've added an electron to 4, to kick it out, you have to lower the energies of the system. You will not get electrons going in and out many times, many hundreds of thousands of times a second, which is how our experiment works, with only small, tiny tickles. So this didn't work. And what you really need to explain this stuff, some kind of degeneracy between that would give you effectively 0 Coulomb interaction between the electrons as you add them. So that you wouldn't get this sort of Coulomb blockade thing, but something else would cancel it out, and you'd get the peaks right on top of each other. So we went on with this and studied it a lot because we thought it was interesting, and we did see like bunches of 3 electrons. This is sort of an intermediate size dot, so it's sort of in between artificial atom and something else. And then we got these sort of double peaks and triple peaks. Then we studied it up here, and what we found actually by building samples with ring gates around them that would gate the edge of the sample preferentially is that the pairing here, as you go up in this spectrum, is actually happening at the edge. And this was really a mystery. 2 other people in this room worked on this and sort of extended the model that Liang had developed to some kind of pairing at the edge. But again, it still didn't really explain this idea that effectively I have to have something that behaves like 0 Coulomb interaction rather than negative U. So we still didn't really understand it. What we did more recently was to make some super clean quantum dots. So these are with no unscreened dopants, and you can start from the first electron here, and this is in a large dot, so big like the other ones. And again, you'll see the first electrons going into traps, and then eventually the thing becomes a blob of metal, and the peaks spacings are very close together, and you're not resolving them here. What was really interesting though was that we could take that dot and go up to thousands of electrons in the system. This is just in comparison to a small, tiny quantum dot that acts like an artificial atom, where you can see filling factor 1, filling factor 2, and this funny sort of zigzag behavior that has to do with depopulating Landau levels at lower magnetic fields. So what we did here is zoom in on a couple places. If you zoom into the integers, nu equals 1 and nu equals 2, you see these little striations going along. Now, these had already been seen before in Amir Yacobi's experiments of putting an SET right on top of a 2D electron system. But what Amir couldn't do, because he didn't have a quantum dot, he couldn't localize, he couldn't look away from integer nu, because electrons could just flow in and out of his system freely. What we did instead with this system, because we have a confined quantum dot, where we can have discrete numbers of electrons in the system, we can just sort of zoom in carefully to different regions and look at the electron additions. Now, it turns out that I don't have time to talk about this, but we're looking preferentially at the edges of the system when we're doing this because tunneling into the bulk involves a kind of Coulomb barrier that suppresses it. So we're looking at tunneling at the edge, and what you see is something interesting. It looks exactly like the interferometry results that you saw yesterday from Philip. And the interesting thing is, if you look at filling factor 5/2, you have a spacing that is exactly half the spacing in magnetic field. And it turns out to be h/2e of flux between these peaks that are going downwards. They're going downwards because these are edge states that move down in energy as you raise up the magnetic field. This is what's happening at 3/2, where you have twice the spacing. So the fact is that we have h/2e flux here. We have h/e flux here, which makes h/2e looks like two electrons acting as a pair. If we looked at the spacings, again, it's a factor of 2 apart, but also if you look at the peak heights of these capacitance peaks, when you're filling factor 5/2, you are getting, again, pairs of electrons. This isn't supposed to happen because electrons are supposed to repel going into the system together, whereas at filling factor 3/2, you get peaks that are 1 electron peaks. So Heidblum had seen this in his interferometers, that there was this thing going on where you had at filling factor 2 and below, actually he was 5/2 and below for him, you ended up seeing h/e oscillations and h/2e when you went to higher filling factors. And now, Phillips showed the exact same thing going on yesterday. Now, what this all has to do with our crazy pairs at low density, I don't know yet. But we did detect that things were going on at the edge. And I think this is probably all like one big phenomenon. There's some crazy glue that we don't understand. There's another group in France that has now seen similar things. So this is a really real phenomenon. It's been seen now in many experiments. I'm excited about it. The people in the room here have thought a lot about these things, and I thought I would bring all this to your attention. Thank you.
Look at some questions to make.
We call this phenomenon elastic blockade, and with identifying this phenomenon with storage of elastic energy in this interacting electrons, and that we figured out that can be 2 or 3 or more electrons can enter together when we discharging Coulomb energy. So what was wrong? You said something was wrong. Something was not working.
Right. So what's wrong is that negative U, what it will do will you'll have some reconfiguration, right, which will shift the energy levels down. And then what will happen is I'm just applying a tiny AC tickle, right? So I have to always stay resonant. I've got to get 2 electrons to go back and forth at the same gate voltage, right? And so what the negative U model does says, I have to turn up the gate voltage enough to get this electron in. And then once I do, there's a shift in the spectrum that shifts everything down, and that guy automatically fills, right? But I can't get electrons to go back and forth.
No, I don't think so. Okay, we should discuss it together.
My story about you, Boris, was that when I first met you, well, I was very familiar with Baronovskii from grad school, and I was amazed by this paper. You came up to me after my big career-making talk in Indianapolis and talked, and I know who you were. And Horst Darmer came up to me and said, "You know who you were talking with?" I said, "No, I have no idea." That was if Skovsky likes it, it's got to be good. Okay, so that's my career. Thank you very much.
My system, but it's not going to be enough that stereo effectives and files. But still that you have to inject the outside. So, not really complicated. That's insufficient.
Okay, so my name is Yi. I was Boris student. Now I'm in Maryland. So today I'm going to talk about recent progress in TMD monolayers and our understanding of the disorder in those systems. So we know recently there's a lot of progress in this TMD system. There's a lot of interesting interaction physics in this system. So for example, people observe Wigner crystal in molybdenum diselenide, either the monolayer one, which is from Harvard, this experiment from Harvard, recently, they measure the optical signal of Wigner crystal. They see the on-club scattering from the periodic Wigner lattice. And there's another paper from Berkeley, from the Wang's group, and they see the Wigner crystal using STM, and this is the image of their STM. It's bilayer molybdenum diselenide, and the dots shows the electrons, while the red dot shows the charge impurities. That's one example of interaction physics in TMD. Recently, Corridin also make a good progress in tungsten diselenide, and they see for the first time multiple fractional quantum Hall states in transport of tungsten diselenide. Previously, they can only observe it using either capacitance measurement or optical measurements. Also, there's a very exciting progress in in fractional quantum Nernst Hall effect in twisted molybdenum ditelluride. The same system Alan McDonald was talking about yesterday. As you can see, the plateau here is not perfect. Also, the dip of RXX is also not that impressive compared to our gallium arsenide, for example, in quantum Hall effect. But still, we see the effect. This implies there's some dirty things inside of this system. So that's one of my motivation to understand what's the possible disorder in this system. And there are other interesting effects like Kondo lattice. This work is done by Kim Weiss group. You can see all the localized spin and the itinerant electrons going on top of these localized spins, and there's some interesting physics there. And also there are interesting things about external insulators, and this work, this beautiful figure I was taken from one of Allen's reviews paper. So there's many things going on in this material system. However, this system is strongly disordered, which is characterized by its low mobility. It's only a few thousand for the chemical vapor transport samples. This plot I was taken from, I take this plot from Philipps paper. They recently measured the mobility in two different samples. This is the mobility for the CVT sample. And as you can see, the highest mobility at lowest temperature, different colors indicates different temperatures. The lowest temperature mobility is only like 2.5 thousand.
Which material is this?
It's tungsten diselenide. But similar things happens for other TMD materials. Although von Kleesing yesterday told me that he observed the quantum Hall effect for 4,000 mobility samples. So this resembles the history of quantum Hall effect. If we can improve the samples quality, maybe we can discover many more interesting physics in this kind of system. So another evidence for this system, which is strongly disordered, is from the STM image I just showed you from Berkeley's result. So as you can see from those red dots here, you can estimate the density just from this image. You count how many red dots here and divide it by the area. And the answer for the impurity concentration here is 3 times 10 to 11. So that's a lot of charge impurity concentration. And one of interesting thing here is they see the Wigner crystal at a very high concentration, 10 to 12, which corresponds to RS, the parameter RS, maybe like 1 to 10, not very high, but they can still see this sharp dots of electrons. This means they said this means electrons are the Wigner crystal are pinned by disorder charge impurities. And they show even the image of this this image of the maps of Wigner crystal, and some regions are liquid, some regions are pinned Wigner crystal. So this means there's an interplay between strong interaction and strong disorder physics in this system if we go to not very low, even if we go to not very low density. So recent advance in these materials is done by a new technique, which is called the flux form technique, synthesis technique. So in using this technique, also I should probably explain what this technique is. They use different flux density for the transition metal and the selenium atoms. So if they increase the ratio of W compared to SE, they find that they can decrease the defect density by a lot, like even 2 orders of magnitudes. So for example, here is the STM image. I take this image from James Holmes and Goridin's paper. So this is the image for the ratio of 3 to 1. And the bright dot shows the charge impurities. This is the zoom in of it. And as you can see, by increasing the ratio of the flux density, the charge impurity density decreased a lot. And using this method, people can now achieve very high mobility by increasing by two orders of magnitude. Previously, it's a few thousand. Now they can reach almost like 100,000.
Do you imply that disorder is vacancies, selenium vacancies?
Yes, they can also observe vacancy here, but the resolution is you should increase the resolution to see the vacancy. I think probably D, E, F are showing the vacancy. Yes, D, E, F are showing the vacancy. The A, B, C are showing the charge.
Flux method gets rid of vacancies, or
they cannot get rid of the vacancy. The vacancy density is like 10 to 10 for this technique. Yes. The charge impurities density is like 10 to 9. So by Ni, I mean the charge concentration, charge impurity concentration. And V means the vacancy defects. So there are 2 kinds of defects in this material. One is charge. The other one is not charged. The charged one can be seen from the contrast of the STM. For the vacancy defects, it's charge neutral. So you cannot see from directly from the contrast that much. but you can see this small dot here. This is extremely short range. If you zoom in, you can see it's exactly 1 atom size. So here I show you the result from Philipps group. So this is their mobility density curves. Different colors indicates different temperature, and at lowest temperature they can reach like 30,000 for mobility. And for the Corridin sample, these thick red lines, they can reach 80,000 at lowest temperature. And if we compare these mobility density curves to other systems, definitely it's uncomparable to gallium arsenide. Gallium arsenide is in this range, so it's like 2 orders of magnitude higher than the TMD materials, but it already beats the silicon MOSFET. The advantage of this kind of material is that because the dielectric constant for this material is smaller. So gallium arsenide has dielectric constant like 13, but for TMD, the dielectric constant is determined by its environment, which mostly like HBM. The dielectric constant is 5. So it increased the Coulomb interaction by decreasing the dielectric constant. So the screening is weaker. Also, the effective mass in TMD system is much higher than, for example, gallium arsenide. Gallium arsenide is 0.067, but for TMD, it's usually like 0.5, like it's the same order of the free electron mass. So this greatly increased the range of RS for the accessible density experimentalists can reach. So this means we can probe the interaction physics more in this kind of materials, similar to zinc oxide. I should mention there's another famous work of Wigner crystal observed in zinc oxide. So another comparison for this material to other material is that because TMD monolayers is atomically thin, so there's no surface roughness as observed in other kinds of semiconductors like gallium arsenide. So for the other kind of semiconductors like gallium arsenide, the highest mobility is often limited by the surface roughness. This actually was explained by one of my papers in Boris 2 years ago. So we analyzed the best sample Lorentz fiber has, and we use Boltzmann transport theory to calculate the mobility as a function of density, and we found that for this kind of sample, the highest mobility is limited by the interface roughness, and it agrees with the trend of thickness to power 6 predicted by interface roughness scattering. As you can see, this line it's the upper bound for all these materials mobility. So one natural question is, if there's no surface roughness, then what limits the mobility of TMD materials for high density? What's the reason that this material has a saturation mobility? So I will explain this in my talk. So here I show you the experimental data from Columbia School and the Harvard School. As you can see, one distinction is that for Columbia School data, their density is 1 order of magnitude lower. The lowest density they can achieve is 1 order of magnitude lower than the Harvard sample. This is because the context is better in Columbia sample than the Harvard sample. So essentially, in Harvard sample, the contact resistance is so high at this density, so all data collapse here. So because of that, I will focus on the Columbia sample in the rest of my talk. So if you look at the mobility as a function of temperature, you can see that at lowest temperature regime, like between 1 to 10 kelvins, is quite flat. But as you increase the temperature, it decreases. So this indicates that electron-phonon coupling enters when you increase the temperature. In my talk, I will focus on the disorder scattering mechanism, which limits the mobility in the lowest temperature range. Here I show you the by the solid disk, the mobility at the temperature of BG, the BG temperature, which indicates the characteristic temperature scale of electron-phonon coupling. As you can see that the mobility collapsed roughly around this temperature, which indicates that indeed it's electron-phonon coupling. If you go zoom into the low temperature, we can look at the data from Columbia sample. So they claim they see a metal insulator transition, although their contact resistance strongly increased at the lowest density, around 1.6. So they don't have very reliable data in this range. They even cut the data for lowest density for this density, for lowest temperature for this density curve. So they see that the derivative of resistivity as a function of temperature change sign at roughly the density equal to 1.6 times 10 to 11. So they claim this is their critical density. And because at this density, RS is roughly equal to 30, they think it's probably Wigner crystal transition. However, we also see that at this density, at zero, if you go to zero temperature, the resistivity goes to roughly E squared over H. This usually indicates that disorder induced Anderson localization will also gives rise to roughly equal number of critical resistivity at E squared over H. So again, this indicates there's a strong interplay between disorder and interaction in this kind of system. But my focus in this talk is not about the metal insulator transition part or the insulating part. I will focus on explaining why the resistivity has a linear in T temperature dependence for the metallic side. Another evidence showing this sample is good is from the fractional quantum Hall states observed in this sample. So here's the Landau fan for this sample. You can see there are many fractional states in this sample. There's even a dip in the even denominator, three half states. Also, the gap size is quite big compared to gallium arsenide. So for gallium arsenide, it's usually 100 millikelvin per scale. So I will come to the disorder model for this kind of system. So in experiment, this system is encapsulated by two dielectric medias, which are usually HBN. There are some background impurities which are charged inside of HDN. And there are vacancy defects in TMD materials. Also a small amount of charge impurity defects. But I don't distinguish the in-plane charge impurity defects to the background charge impurity defects in this talk. Also, there are remote impurity defects locating somewhere in the HBN, because usually the remote impurity defects in this stack structure locates close to some interface, and the only interface here are the gate and the dielectric interface. So in my modeling, I assume that those charge defects are somewhat close to the gate. At t equals 0, one thing we observe from previous data is that the mobility increase as a function of density. This is because if you increase the electron density, then those free carriers can screen the disorder, the charge disorder a lot. So in this sense, mobility can increase. However, we also observed that at high density, mobility decrease. So there's a non-monotonic behavior in these mobility density curves. I would argue later that this is due to the charge neutral atomic point defect scattering. So I use Boltzmann transport theory to calculate the mobility density curves. So for remote impurity scattering, because the momentum transfer is small, so the dominant scattering angles between the incoming electrons and the outgoing electrons is small, and it's usually limited by the how far the impurities are from your 2D electrons. So in our case, if the distance from remote impurities to the 2DAC is d, then the scattering angle is roughly 1 over k Fermi d. And from the Boltzmann transport, there's an extra factor in the transport mobility, which is 1 minus cosine theta, as known as the vortex correction. So there's an extra theta square if theta is small coming into the expression. So as a result, the final mobility result from the remote impurity scattering will be proportional to k Fermi d cube. And this results into a mobility which is proportional to the density of to power 1.5. For background impurity scattering, the most dominant one are those impurity close by to the 2DACs. And you can think of the thickness of those close by impurities, which dominates the scattering, as 1 over 2k Fermi, which is the wavelength of the electrons. So the effective density which enters in the dominant scattering events is the 3D concentration of background impurities divided by k Fermi. And this results in a smaller density dependence, which is n to power 0.5. For in-plane impurity scattering, they scatters the strongest. So if there's a 2D concentration of in-plane charge impurity, Ni, it doesn't depend on the density at all. And lastly, for the highest density mobility, the dominant scattering mechanisms are those charge neutral point defects. This can be seen from a very simple derivation. So I actually first look at Philipps' paper and look for what's the possible scattering calculation resulting from those charge neutral point defects. And the theory collaborators there using a very complicated methods beyond the Born approximation. They calculate a lot of diagrams to calculate the scattering rate for charge neutral point defects, because the charge neutral point defects, they think the potential is very high. The scattering potential is very high, so it's not captured by the Born approximation. And they write very long paper, theory papers several years ago. I look at that papers and I summarize this paper's result in 2 lines. So those beyond Born approximation results can actually be captured not from quantum mechanics, but from classical mechanics. That's one of the greatest thing Boris taught me. So for vacancy defect scattering, if you think of it classically, the scattering cross section is a constant. It's just limited by the size of the point defect. If we use it as an assumption, then you can derive the scattering time immediately just from the definition of scattering cross section and the mean free path. And you found that the scattering time is the scattering rate is proportional to V Fermi, and that leads to a dependence n to power -1/2, and this explains very well the high density behavior of these mobility curves. Yes.
Just a simple question. So we know that encapsulated graphene has very high mobility. If I understand correctly, the remote impurities that you're considering are coming from the boron nitride encapsulation. Is that correct?
It's possible because I remember from one of my experimental collaborators, they are doing experiments by changing the gate materials. And by changing the gate materials from, for example, gold to graphite, few layers graphene, they see change of their results, their transport results, by a reasonable amount. So it's not a small change. So this means the gates some defects around the gates can affect the transport data.
Sure. Okay, yeah. But my question maybe is, if you compare to isolate these different contributions, you can compare graphene versus TMDs with the same setting, like let's say graphite gated, same BN, same groups. They know how to do it very well. And then, does it make sense to consider these defects for these to explain these experiments, or it should all be within the TMD layer? The difference.
Yeah, I think it's reasonable to consider other structure because the gate defects doesn't depend on your material encapsulated inside. But another thing to verify is simply just, for example, you can increase the thickness of HBN and see whether this improves your sample quality.
Similar question. The guys, so what's the difference between the TMD mobility and, for example, graphene's mobility? Because they're using like the same setup, HBN and graphite. It looks like graphene can have much higher mobility than TMD system. But does that mean the TMD, the charge neutral defects or the impurities in TMD limits the mobility of those samples?
I think yesterday I heard from Philipps that for graphene, the limiting scattering mechanism is the size of the graphene because the mean-free path is already much larger than the size of graphene. So
yeah, I think one thing I can also point out, the effective mass here is much larger than effective mass of graphene. So if you just think about it in terms of mobility, I think there's already almost order, maybe 2 order of magnitude even difference.
What if you think of bilayer graphene, low density?
It's a kind of similar still. I think, but if you just kind of look at the effective mass of the bilayer graphene with the typical doping, it's much smaller than the TMD case.
Yeah,
I think the question is kind of good questions. I don't know whether if you just can do the similar calculation with the graphene, whether you will get the similar amounts of this remote impurities.
Yeah, that's
some of the charged impurity boron nitride. What is the effect of that into the graphene mobility? That's a good question.
Yeah, that's a good question. I haven't looked at the data of graphene yet. I will look at it in the future.
Potentially, the cross sections can be. I think those effect onto the effective cross section giving into the graphene can be quite different. Various reasons, but
right. For example, in bilayer graphene, the electron mass there, I think if I remember correctly, similar to gallium arsenide, is 0.041. So this will change the results a lot. I have to redo the calculation and see what happens.
I have questions on today that what is this large sigma indicating there, the charge neutral point, the defects? When you say that this T matrix can be approximated in the simple arguments, what is the large sigma? That's cross section.
Yeah, that's the cross section. That's has a union area. So it's in my calculation, I just set it as the size of the lattice constant square. Yeah. And also, if I use this theory, I predict vacancy density in agreement with what James Hom and Corridin saw. they see roughly 10 to 10, between 10 to 10 to 10 to 11. Yes.
Yeah, just understand. So what are the limiting bottleneck for the mobility? Is it remote or is it in-plane?
So I think it's remote because the density dependence is very close to 1.5 at low density. In gallium arsenide, it's background impurities because if you look at the density mobility density curves there, it's close to 0.6, if I remember correctly. So for gallium arsenide, it's background impurities, but for this sample, I think it's remote impurities, likely.
Oh, it's on the boron nitride or?
Remote is at the boron nitride gate interface, close to that interface. Yeah. Also, I talked to Michael Manfra that because he knows everything about gallium arsenide. Because I was challenged by Faridin that my sample is very good. There's no defects at that interface. And Mike Manfra look at this data and see this mobility density dependence. He said, well, it looks to me it's very likely remote impurities. So maybe Faridin should increase by getting rid of this kind of defects and increase his sample mobility.
So this is graphite gated, right?
A few layer graphene gate.
Yeah.
Yes. So I also did the calculation for finite temperature. So in the calculation, I include the temperature in two steps. One is from the dielectric function, which requires a temperature dependence. Essentially, the screening will be different for different temperature. And the second is when you have a finite width of temperature, then you need to do an energy average over the Fermi function. So here is the result for my comparison between experiment and the theory. As you can see, although not quantitatively exact, it captures the trends. Like the mobility would decrease by increasing the temperature. And the peaks where the saturation mobility has, the peaks of the density would also shift to higher density if you increase the temperature. Yes. And as you can see, the lowest temperature mobility is quite flat, as indicated by the disorder calculation. And I ignore all phonos in my theory. So I forget to explain the line, dash lines here. So this red dash line indicates the slope 1/t. And the other blue lines indicates a higher slope. And it's just experimental range that the slope allocated. So lastly, let me explain what's the mechanism for linear resistivity from the metallic side approaching metal insulator transition. So we know that for two-dimensional screening, there's a kink of the polarizability function at the backscattering momentum 2K Fermi. This is because if you increase the scattering momentum, the two Fermi surface of the 2D electron gas will detach from each other at exactly Q equal to 2K Fermi. And at that moment, the empty state and the occupied states have the same numbers, no matter how much you shift the scattering momentum. However, the energy difference between those states are keeping increasing. So it's like you are looking at a band insulator and increasing the band. By increasing this energy difference, you are decreasing the screening. So indeed, if you look at the polarizability function, there's a kink at 2K Fermi. If you have finite temperature, then you can reach the states above 2K Fermi. At that moment, the charge impurities are not well screened. because of the fact I mentioned about. And that would increase the resistivity by some amount. And this picture can also be explained by a coherent scattering from the Friedel oscillations at finite temperature, as pointed out by Elena a few decades ago. So the picture is that if you transform the momentum space screened Coulomb potential to the real space, you will see that the contribution of this kink will result into a Friedel oscillations in real space. So this is a schematic pictures of these Friedel oscillations, and that's a correction to your usual Thomas Fermi screening. And electrons if electrons are doing backscattering, then there's a coherent scattering because of this periodic Friedel oscillation structure. And the coherent scattering will enhance the scattering probability and leads to an increase of resistivity as observed here. Another understanding of this picture is that if you do a small temperature correction to the screening polarization function, you will find that the correction is proportional to square root of t. On the other hand, if you are integrating over the scattering angles, you will find that the relevant scattering angles is around also square root of t. So the final correction to the transport scattering time will be proportional to square root of t squared, which is linear in t. Yes.
So a dumb question, but if you have a Galilean variance, so you're using electron scattering, then it's linear resistivity.
Electron impurity scattering.
Electron impurity scattering. I see.
This is the Friedel oscillation from the charge impurity. Yeah, it's not from electron itself. I ignore all electron scapes.
And then will this hold also away from the metal infra transition, or is it only near the metal infra transition?
It works actually better away from metal infra transition to the metallic side.
So
but the resulting correction would be proportional to T over E Fermi. So if you increase the density to the metallic side, this slope will be smaller and smaller, and
okay, thank you.
You cannot observe. Yes. So if I do this kind of calculation theoretically, this is my theoretical result. So you can see that there's an increase of there's a linear in T temperature dependence of the resistivity, but as the temperature goes to the E Fermi, so the electrons becomes more like a classical gas. Because if temperature is larger than E Fermi, then we don't care about whether this particle is fermions or boson, and everything is described by the Boltzmann probability factor. And in that case, because electrons are running fast, they cannot screen the charge impurity well if you raise the temperature, and in that case, you will see that resistivity would decrease as a function of temperature. So one of outlook of this of my work is to help experimentalists improve the mobility. So if indeed the dominant scattering mechanisms are from the remote impurities close to the gate, then one simple way to eliminate them is to increase the HBM thickness. So here I show you an example by the dashed lines, the result by doubling the HBM thickness, and the mobility can increase from 8 to 12. I should mention that in Philipps sample, the HBM thickness is much higher than Corridin's sample, but because of the contact issue, they cannot measure the mobility to very low density. But if I look at the trend of your data, it seems like it should keep growing at lower density.
If I make one more comment on there,
I think the sample that we received from James on is the 1 generation older sample than what Corey used more recently. So I think
So this one is even better.
Corridin sample that reported is probably state-of-art sample. Intrinsic impurity distribution might be also kind of quite different.
Okay. Here is the log plot, and you can also see that the slope of this low density mobility is very close to 1.5, which is shown by this remote impurity curves, the red lines here. So that's another evidence, more obvious evidence. So another outlook is to look at the Wigner crystal melting in this kind of system. So they haven't done very prudent. I should probably not say prudent. They haven't done work on Wigner crystal in this new kind of generation of TMD system. All these old experiments are done in old generations of samples with very large density of charge impurities. So if they repeat the experiment in, for example, in tungsten diselenide, I think they should see better results. So here is the mean field phase diagram of quantum Wigner crystal, which I was taught by Boris. So there should be a dome of Wigner crystal in the temperature and density phase diagram. So it should be understood as if you increase the density, then the quantum fluctuation increase and Wigner crystal melt. If you increase the temperature, then thermal fluctuation increase and the Wigner crystal should melt. And you can estimate what's the critical density and what's the critical melting temperature in this kind of system. And you will see that they for density is proportional to m squared over kappa squared. Forgot to write it here. The temperature is proportional to m over kappa squared. So for TMD materials, because it has lower dielectric constant and higher mass, so the phase of Wigner crystal is larger in this kind of system, and that makes this system more probable to be observed Wigner crystal in extreme. Okay, yeah, that's a comparison to other material system. I will skip this. So something we can do in the future, probably if they can keeping increasing the contact for this TMD system, then they can reach even smaller density data. And we can study maybe hopping conductivity in the insulating phase. Also, I haven't talked about any theoretical work related to their magnetotransport. So in the future, we can also study that. Another disorder I haven't discussed in TMD system is the for twisted moire system. There's always disorder related to the difference of twist angles, and there are domains of different twist angles in this kind of system, and this can also lead to some experimental consequences. So thank you, and if you want to look at the details, you can check my paper.
Again about TV.
Okay, so it's a simple, quick question. So, what is the scaling? How does the mobility scale with the infrastructure? Right? Is there a formula, or does it depend linearly, or?
If it's remote impurity scheduling, then it should be equal to
Yeah. Again about this TV near resistivity. I'm trying to think about ways to distinguish this with other mechanisms. Proposed a lot of, there are a lot of proposals.
Yeah. Like
so one question I have is like, what about like the mass as you go to the low temperature? Is there any increase of the mass within this theory? Because some other theories predict the mass of the increase as you approach the metal ink transition.
Yeah, I think I remember one measurement maybe by Kim Bai in the Kondo lattice paper, measuring the mass approaching the metal insulator transition, and there's the effective mass are different. I think that those measurements are indirect.
the theories. You cited the theory about coherent scattering from without state.
If the mass increase, then the Fermi temperature, because Fermi temperature is proportional to 1 over mass, and the correction is linear in T over E Fermi. So the correction should increase. Yes.
Yes, that was even getting back
I haven't read it. Yeah, my goal there is just to use screen charge to see whether I can explain everything.
Yeah, I mean, if there's a outcome case, simple explanation.
Yeah.
Good data for getting last team entities. And I was just asking, it's boundary don't know.
Not sure. I'm not sure.
He's now a professor in John Hansen.
Oh, Boston. Oh, Boston. Okay, sounds good.
So he is.
Yeah. I have.
Okay, sounds good.
Yeah.
He has done that. So somewhere he's more specialist.
Okay, that sounds good. Yeah. Because just as Laurie said yesterday, we are very interested in this transition from crystal to quantum Hall. So I'm trying to so you made a comment yesterday about the level mix. Yeah, that's true. Yeah, I know that. I know that. So we are very interested. Yeah, I'm very interested in this. Even fitting factor. If they are fixed fitting factors, increase magnetic field and increase its caution. Then a high field, high density will be the small field and small densities. You get the explanation. And this is crucial to rely on the level mix. But without the level mix, the integer thing is always constant.
Oh,
very interesting.
就是我做实验，他讲的可以这个，这个大概会要蛮否的，就是我看像他们做的比较好的，我自己观察了一下他们那群，
因为它硬了嘛，太厚了。
我也不知道具体原因是什么，我只感觉这是一个经验总结，就是它厚了它掉了一点。
还是说你 pick up 的时候它会分成2层？
啊，它不会分成2层，就是你看我这种 HBN 底下那个 HBN。如果我的 HBN 比较厚，我需要到更高的水水，我觉得它更容易废，更容易 pick up 起来。就我一个比较薄的话是
更高的 temperature。
对对对，更高的，因为我是用那个用胶，用 PC 或 PVC，然后让那个它慢慢的融化，让 HBN 贴到 HBN 上。如果 temperature 太低的话，它那个胶是比较硬，就相当于因为
它就粘不住。
它虽然不是胶，因为那个胶很硬，所以它不能很好的贴合到那个 HBN，因为它有个 finite thickness。如果胶比较软，它可以变形。 教的那个 HBM 把它会 HBM 的表面，它都可以变形，慢慢的就让那个底下的 HBM 它
就跟贴手机贴。
对对对，模。他们做的比较好的短命的 sample， 他们都是用20到30 HBM， 就那种。就是我不知道他的那个华润定和飞利浦上用的 HBM 做的。可能就是做这些 sample 的学生，他们没有考虑，就是 HBM 不能还有。但有些其他的方式，就是他们做一个 HBM 包着 HBM， 然后他们 anneal， 然后再用 AMP， 就是那包的 HBM 已经在我 gate 上或 substrate， 然后他们再打下它的 node， 那个可能会有好，但是我觉得这种方法还是不如直接 pick up HBM 要干净，因为它多了一个 step，
多了一个 step 就会引入一些新的脏的东西。
对，不太确定。
然后那个 Sandip 和 Foster 要跟我一起。
好。
We just go outside and see what we can get. So.